Okay, before that I start my my lecture for this week, I'm going to introduce to you or refresh with you some what we had before, and also at the same time to define what's meant by K-map. Let me start now. If you have three inputs, x, y, z, okay, and you know exactly if you have three inputs, this means that you have three inputs, okay. Means what? 3 inputs means that you have 2 power 3, which means that you have 8 combinations of 8 different rows. Actually, you have here start from 0 1, 0 1, 0 1, 0 1, and then you have double zeros, double ones, double zeros, double ones, and then you have at the end 4 zeros and 4 ones. Okay, why is that? Because you know exactly if you have here the first column, corresponds to 2 power 0, which is 1, the second column corresponds to power 1, which is 2, and the third column corresponds to power 2, which is 8, which is 4. Actually, we have here the weight of 4 to 3, so this is why you have here only one change, 0 1 0 1 0 1 0 1, and then you have double change, double zeros, double ones, double zeros, double ones, and you have here 4 zeros and then 4 ones. This is what we call here the truth table of your function. And also you have also to define the relationship. The truth table is a relationship between in and out. So here you have function out, function f, which is the output for you, is equal what? Equal either sum of product, or you can write it in a product of sum. Sum of product means what? That you have here f equals summation of product term when f equal to 1, and product of sum means f equal pi multiplication of some terms when f equal to 0. What is meant by product term and sum term? You know exactly if you have x, y, z like that, you have to define what's called p and what's called s. P is a product term, s is what is the sum term. P, whenever you have 1 is true and 0 is false, okay, and s equal 1 is false and 0 is true, which means what? If you have 0 0 0 underneath x, y, z, this means that you have 0 is actually here is false and 0 is here is true. So if you're talking about product term, you have to multiply. This will be x bar, y bar, z bar, and the other one will be what? X plus y plus z. Okay, so this is actually how to define the product term and sum term. And then the second one will be x bar, y bar, z, and this one will be x plus y plus z bar, and you go on until you have here at the end x, y, z, and this one will end up with x bar plus y plus y bar plus z bar. So actually this is what we meant here by a value of the corresponding product term and sum term, and then you can just here to define the functionality, the sum of product and product sum of the function. Now let me introduce what's meant by a K-map or Karnaugh map. The K-map is actually going to represent the truth table in a form of cells. Form of cells like what? As long as here you have 8 cells. 8 cells means what? You have line 0, line 1, line 2, line 3, line 4, line 5, line 6, line 7. You have 8 rows. So each row here in the K-map will be represented as a cell. So you have to define your cells like that. This will be 1 2 3 4 5 6 7 8. You have 8 cells here. Each cell corresponds to what? Corresponds to one row inside the truth table. So actually each cell corresponds to one row inside the truth table. Okay, so this is what we call here. If you need to count the number of cells, you have also to define what's meant by the variable x, y, z. So if you go to orientation x to z, from left to right, so you have to say here I go from x, y, z, from left to right, the same direction. So the orientation is very important. X is your left and z is your right. Why? If you have here x, that's two values, either 0 or 1. So 0 means that this row is x equals 0, 1 means x equal 1 for this row. For y, z, you have here 0, y is 0, z is 0, y is 0, z is 1, y is 1, z is 0, y is 1, and z 1. So actually what we have here, you have mapped the values of x, y, z. Here x equals 0, y x equal 1, and this one you have x 0 and y 0. Sorry, y 0 and z 0. Here you have y 0 and z 1. Here you have y 1 and z 0. Here you have y 1 and z 1. So actually what you did, you put all the values of your x, y, z. At the same time, you have here 0 0 0 corresponds to what? This is cell 0. So actually cell 0 is 0, 0, 0. Cell 1, 0, 0, 1, which is this is cell 1, cell 2, cell 3, cell 4, 5, 6, 7. So each cell represent the row of your truth table. So actually what we have here, this number corresponds to row number 0, row number 1, row number 2, row number 3, 4, 5, 6, and 7, and so on. Also inside this cell, you can write down. You can write down what? Either the product term, which is here, is this one for this cell, is x bar, y bar, z bar, either the sum term where x plus y plus z, and also you can put the a value, the f value, which means the output value. So inside the cell you can write down the product term, you can write down the sum term, and you can write down the value of f. So actually this is the definition of what is called the K-map. But this definition here is correct by mapping 1 to 1, but actually this is wrong. Why is wrong? Because for the K-map has some rules. The first rule, any adjacent cells should horizontal or vertical. Okay, you have only one digit changing value. Changing value means what? One digit changing value, if you go back here, you have 0, 0 goes to 0, 1, which means only you have a 0, 0, and 0 is 1, so you have only one change. But if you go from cell 1 to cell 2, you have 0 goes to 1, 1 goes to 0, this is a violation, which means that you cannot do that. So actually 0 goes to 1, it has a double changes. Double change mean what? This is forbidden because you have 0, 1 goes to 1, 0. Double change, which means this is forbidden because you have to have only one digit changing value. So violating the rule of the K-map. So this is actually completely wrong. So we have to modify and do some changes to the K-map in order to match this rule. So what we should do? You will have the same cells here. There's 8 cells. And actually the same orientation, you have x, y, z, okay, and you have 0, 0, 0, 1, 1, 1, 1, 0, and here 0. What happened here? I have swapped between 1, 0 and 1, 1. So actually there's a swap between these two columns. I made this this column goes there, and the other column A goes back, and this one, the swapping here, made some changes in the values of the rows. As you can see in this figure here, you have here row number 0, row number 1, and then 2 goes where it goes there, and we have 3, and then 4, 5, and 6, 8, and 7. So actually what is going on here is that you have changed the orientation of the rows in order to match the rule here, only one digit changing value. So this is actually what happened in the modification of the K-map. So now let me now start. This is what we did, that in order to, at the end, we need to get the optimized solution. Optimized solution means what you need to reach the optimize the minimum variable or the minimum equations that you can reach. So by doing that, this is actually what you call the reorientation of the rows inside the K-map in order to reach a certain advantage you're gonna see in next. Now, if I'm talking about if you have 4 inputs, you have A, B, C, D. 4 inputs means what? 2 power 4 equals 16, which means that you start from 0, 0, 0, and you end up from 1, 1, 1. So you need to start from row 0 to row 15. So in order to draw also the map for this one, you are going to have 16 cells like that. This will be the 4 input maps. At the same time, if you go orientation from left to right, so you have here A, B, C, D, and you have this one, you have what? 0, 0, 0, 1, 1, 1, 1, 0. This is swapping between this column and the other one. At the same time, you have here 0, 0, 0, 1, 0, 1, 1, 1, 1, 0. It did a swap between these two rows. So actually these two rows are swapped and these two columns are swapped. So actually what happened here, you have made a swap between the two columns of the two rows in order to match the rule of this rule, which says only one digit changing value. So actually if you go back here, you will have row number 0, row number 1, 2, 3, 4, 5, 6, 7, and then you have here 8, 9, 10, 11, and then you have 12, 13, 14, 15. This is actually the new orientation of the 4 input K-map. So as you can see, we have 2 columns swapped, and we have 2 rows swapped to each other. Okay, so this is now another rule of the K-map. Another one, if you talk about now, is the K-map in 3 dimensions. You said that this is adjacent horizontal, and adjacent vertical. At the same time, if you think about it in 3 dimensions, you found out what? If you do it folding like that, folding like this way, you'll find that this row is adjacent to this row. So actually these 2 rows are adjacent to each other if you fold it in this direction. And at the same time, this column is adjacent to this column if you go in this direction. These 2 are if you swap it and fold it in this direction. So actually you have these 2 rows are adjacent, these 2 columns are adjacent. At the same time, the 4 corners are also adjacent if you fold it in different directions. So actually you have these 4 corners are adjacent to each other. So this is another rule of the K-map, that you can have the first column is adjacent to the last column, and the first row adjacent to the last row, and also the 4 corners are adjacent to each other. And you can find that when you talk about the example next in the lecture here. Okay, let me now find out how to find what f is equal to. Now let me give you example. If you have the 16 4th input again like that, and you have again A, B, C, D, and you have this one 0 0 0 1 1 1 1 0, and here you have 0 0 0 1 1 1 1 0, and this is row 0, row 1, row 2, row 3, row 4, row 5, 6, and 7, and here you have 8, 9, 10, 11, and then you have 12, 13, 14, 15. This is actually what we have as a numbering of system. Assume now we have F1. F1, I have only 1 here. So F1 equal what? If you have only 1 here, this means that you have this cell is active and the other cells are 0. So actually F1 equal the value of this whatever the product term inside this cell. The product term inside this cell is what you have 0 0 0 0, which means that equal what? A bar, B bar, C bar, D bar, because we are talking sum of product where 1 is true and 0 is false. So actually what you have here, F1 equal A bar, B bar, C bar, D bar. Again, this is a function for this F1. Assume now I have another one here. This one will give you what? F2 will equal this term plus this term, which means that A bar, B bar, C bar, D bar plus this term is what? A bar, B bar, C bar, A, D. So you have A bar, B bar, C bar, D. So as you can see here, I can have A bar, B bar, C bar as a common term. So I will have A bar, B bar, C bar as common, and multiplied by D plus D bar, which is equal to what? Equal to 1. So actually it will be A bar, B bar, C bar. This will be the value of the function if you do it by equations. But now there's another thing about the K-map. The K-map gave you what's called groups. You can do groups, but these groups are 2 power n, where n equals 0, 1, 2, and so on. Which means that you have group of either 1 cell, or 2, or 4, or 8, or 16, or 32. So because it's 2 power n, you have a group of what? Group of 1, 2, 4, 8, 16. You cannot have a group of 3. You cannot have a group of anything else except 2 power n, where n equals 0, 1, 2, 3, and so on. So this is actually another rule of the K-map. You can have groups of 1, but you have to have what? Maximum number of ones. You have to find the maximum numbers of ones to do groups. Okay, the groups are doing like what? It's actually, the groups are any adjacent cells. Okay, any adjacent cells of a group of a maximum group of ones, okay, but they are horizontal or vertical adjacent. You cannot have a diagonal adjacent. It's actually vertical or a horizontal or vertical adjacent. Okay, and select. You have to select the variables that are not changing A values. You have to select only these variables that are not changing values. Okay, and neglect those variables that are changing values. Any variable changing variable, ignore it at once. I have to again, you have to have it again. The values, you have to take a group, adjacent groups of horizontal or vertical of the maximum number of ones. At the same time, select only variables that does not, or that are not changing values, and neglect all variables that are changing values. As you can see here, if you go back to this example here, you have 1 and 1. 1 and 1 is this is a group of 2. Group of 2 means what? Group of 2 means that you have to have to find out which variables are changing values, which values are not changing values. So as you can see here, A and B are fixed, are not changing values. So you can have what? This group will give you A bar, B bar. At the same time, you have C not changing value, so it means that you have C bar. But D is changing value, which means that you have A to neglect. You have to go back here and neglect what? Neglect those variables are changing value. So actually D is out. So this means that you got the same answer like the one you got from the equation. So actually the K-map gave you a way in order not to do the equations. What you are just selecting this group which corresponds to we are selecting only these variables who are not changing value, and ignoring the only variables that are changing, which is D in this situation. Another way of getting, and I say if I have another one here means what? I have FC. FC equals what? I have first to select the maximum number of groups. Maximum number of groups, I have here group of 2, this 2, which is actually we have it before, like A bar, B bar, C bar, plus. I have another one here. Should I take it by itself, or I have to maximum number is what? I can take this as a group 2. As you can see here, the K-map gave you another advantage, that you can have this one is a overlapped. Overlap means you can use this one with this group, and they can use the same one again with the other group. So this is actually an advantage of the K-map. You can use either one twice with this group or the other group. This group gives what? This one group, if you can see it, is equally A bar, B bar, which is a not changing value. C is changing value at this time, so C is out, and you have here what? You have G. So this would be the equation for FC, which is at the end equal A bar, B bar multiplied by C bar plus D. At the end you have this type of equation. Remember that if you do it in a way that we discussed before in our lectures, they have 1, 2, 3, 4 terms. You have to add 2 4 terms and then use equations, identities, in order to reduce the function to its optimized form. But here in no time you got the function by doing the grouping, as you can see. Now let me talk about now if you need to get F4. What's F4? If I have one here, this one is what? This one I have 4 terms. I can do 4 terms and then reduce it by equations, or I can have group of 4 because I have the right to get a group of 4. Group of 4 is what? You can see C and D are changing values, but A and B are not. So actually C and D are out, and then we have what? F4 equal A bar, B bar directly from the table. So actually here the K-map gives you directly A bar, B bar, while if you're going to do it in standard way, you have 4 terms and you have to use equations in order to reduce them and so on. So actually what happened here, F4 equal A bar, B bar. Let me talk about another. If you have one here, what happened if I have one here, and this 4 of course exists. F5 equal what? F5, you have this 4, which is A bar, B bar, and then you have this one. Should I take it by itself, or I have now an opportunity to as a folding? This one is adjacent to this one, so actually I can take this group, this one with this one will give me what? Will give me B is B bar plus B bar, because A changing value, and you have here C bar, D bar. So actually this would be the equation if you take these 5 terms here, and actually this is a reduction that F5 will equal to. Assume for the last one now, if I have all these are ones, I have 4 ones here and 4 ones up. So should I take this as a group of 4, or is it better for me to take it as a group of 8? So F6 equal what? If we talk about now, I need to get F6. F6 equal 6 equal what? If you can see here, you have here these 2 are adjacent, so that's actually group of 8. Group of 8, as you can find here, C and D are changing values, And you have also a changing value, and this actually will not equal b bar because everything else are a and b, a and c and d are changing value, and only d is there. So as you can see here, you have reduced the function. If you have 1 2 3 4 5 6 7 8 terms, and you do it by equations, and you do it by what, you end up with what, with f bar. This is a brief about the K-map, about how to use it, and actually now I can start my lecture to give you examples and give you how to deal with the K-map in your solutions. First of all, you have to understand what are the rules for the K-map. The first rule, each square or cell corresponds to a row of a truth table and to one minimum term of the algebraic equation. So as I mentioned in the video, and that each square represents the row number, and at the same time you can write inside this cell minimum term, which means the product term. If you're saying maximum term, it means some terms, and you can write inside the cell also the value of your output f. As the second rule, only one digit changing value between two adjacent rows and column. If you go from one column or one cell to another, if you go horizontal or vertical, you have to have only one value changing only. So one digit changing value means that you cannot go from 0 1 to 1 0 because this will be double changes. That's why if you go from 0 1, you have to go to 1 1 in order to have only one digit changing values. The third rule, one square represents one minimum term, giving a term of 4 variables in case of the 4 variable map. This means that each square represents the minimum term, which is a product term. If you have 4 variable map, you will get 4 variables, whether it is in their value or in their inverted value. Or if you have 3 variable map, you will get 3 variables, and so on and so on and so on. So actually, this actually was meant that each square that you can write inside is a minimum term, which is a product term. You can write inside the sum term, which is a maximum term, and you can write inside also is a value of f. Again, if you go to the video, you'll find also what happened with grouping. You have two adjacent. If you have two adjacent squares, represent a term of 3 letters. If you have two ones in two squares adjacent, whether it is vertical or horizontal, this means that you are reducing the number of values from 4 to 3 letters. The second rule, rule after, if you have 4 adjacent squares, it represents a term of 2 letters. If you have 8 adjacent squares, it represents a term of 1 letter. If the function is 16 adjacent squares are all ones, this means that f equal to 1. So actually these 4 rules here, we mentioned in the video that if you take the maximum number of maximum groups of ones, you will end up reducing the number of variables or the number of letters in your equation. If you have it by one cell, you get the 4. If in case of 4 variables, you get 4 literal. If you are taking 2 adjacent squares, you will get 3 literal. If you are taking 4 adjacent squares, you will get 2 literals. And if you get 8 adjacent squares, you get only 1 letter. So this means that you are reducing the number of letters per term. And if you have all cells equal to 1, this means that f equal to 1. And when a variable appears within a group in both inverted and non-inverted state, then the variable can be imaged. This means that if you have a group and you have one variable changing value, this means that you have to eliminate or ignore this variable. And next we're going to give you the procedure of how to construct the in this slide, we are going to give you the procedure how to construct the K-map. First of all, you have to have the truth table in order to fill the map. The truth table, you have the relationship between in and out, of course. And then if you are talking about sum of product, you have to look for ones. So look for a where f equal to 1. Second, so you make biggest group possible. Biggest group possible means the number of squares inside each group. The squares in the group should comply with 2 power n, or n equals 0, 1, 2, 3, and so on. This means you can have a group of one cell. It's not, of course, this is the original function. Or you can have a group of 2 cells, 4, 8, 16, 32. So you have to comply with 2 power n, where n equals 0, 1, 2, 3, and so on. At the same time, these groups are adjacent cells, adjacent in horizontal or vertical. You cannot say diagonal. So it's actually either horizontal or vertical in row or columns that you have adjacent cells all covered with ones. If you are talking about product of sum, you talk about the same sequence, the same as concept with zeros instead of ones. But actually now we are talking about sum of products. Any square can appear in more than one group, which means that you can have an overlap. If you have one square with one group, and this square can be used with another group, you can do that. This is what we call the overlapping between cells, and this will be explained in details in the next applications or the examples. At the end, you get the expression for each square, and then you owing all the expressions. So actually, these are the rules of the K-map. First, fill the map from the twos table, look for ones, make the biggest group possible under conditions that the groups are squares in the group comply with 2 power n, where n equals 0, 1, 2, 3. This square should be adjacent cells, horizontal or vertical. They all covered with 1. Any square can appear in more than one group. Get expression for this group, and then all expressions in order to get the function in terms of the variables. This slide shows you full variable K-map. As you can see, we have A, B, C, D, and if you remember the video, you have to go from left to right. It's A, B, C. A will be your most significant, and D will be your least significant. Okay, if you construct the K-map like that, if you go from 0, 0, 0, 1, 1, 1, 1, 0 for CD, and for AB you go from 0, 0, 0, 1, 1, 1, 1, 0, why we have exchanged the last column with the one before in order to meet the rule, which means one digit changing value at a time. At the same time, the last row and the row before, we also exchange these two also together in order to match the rule of changing one digit changing value at a time. So as you can see, the orientation or the number of rows is not exactly the same like what you have in the twos table. You go from 0, 1, and then 3, 2, and after that 4, 5, 7, 6, and then the 8 goes down. You have 8, 9, 10, 11, and 12, 13, 15, 14, which means that the numbering is exchanged based on the rule of only one digit changing value at a time. Inside each cell, you can write the sum of product of product term A, B bar, C bar, D bar, as shown here in this slide, or you can write down the product sum. Sum term would be A bar plus B bar plus C bar plus D bar, because here, if you are talking about sum of product, you are talking about 0 is false and 1 is true. Or if you are talking about product of sum, you are talking about 1 is false and 0 is true. And actually inside this cell also you can write down the value of f. This is what you said before is a construction of a full variable K-map. Also, we mentioned before that if you can have the first row is adjacent to the last row, and the first column adjacent to the last column. At the same time, you have the four corners adjacent to each other. So this means that you have to look for the K-map in the three-dimension situation. I mean view. This slide only to illustrate to you that you are going in three dimensions. So as I mentioned before, the first row is adjacent to the last row. If we are talking about the full variable map, the first row adjacent to the last row, and also the first column adjacent to the last column, and the four corners are adjacent to each other. So actually, this is actually illustrate what's meant by adjacency in the three dimension. Let me start here with the first example. The first example, what you can see, that you have f of a, b, c, d is four variables equals sigma m of 0, 1, 2, 4, 5, 6, 8, 9, 12, 13, 14. These are the positions of ones. So actually, as if I am giving you the two stable, but letting in a sort of the sigma m of the f equal to 1. So actually, this is the positions where f equal to 1. So what you're going to do, you're going to fill the ones inside the cell. You have to construct the cell as shown below. You have A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0 for CD, and 0, 0, 0, 1, 1, 1, 1, 0 for AB. And now we are going to put the ones in their A positions. In position 0 and 2 and 1 and 4 and 5 and 6 and 8 and 9 and 12 and 13 and 14. Now what we did, you have filled the K-map from the twos table. Let me now see the groups. The first group you can see here is what? The first group is this Z1. You have the two ones in both sides, because as we mentioned, the first column is adjacent to the last column. So actually cell 0 and 4 adjacent to cell 2 and 6, and this will give you the first group. If you want to see what's meant by this group, or what is the value of this group, as we mentioned before, if you have a variable not changing value, you will take it as is, or its inverted value, or if you have the variable in changing value, this means that you have to exclude this value. For the A, you can see the A equals 0 in both, which means E is not changing value, but A 0, which means that you have A bar in A for this group. For B is changing value, so you don't have B, you have to ignore B. For C, you have C equals 0 and 1, which means that C is changing value. For D, you have D equals 0 and 0, which means you have here D bar, which means the value of this group is A bar D bar. This is the first group we got from the KMAP. We're getting what? We are getting the red group equal A bar D bar, because B is changing value and C changing value. Second group, we said we can have an overlap. So overlap, which means you have here the yellow group, where you have you choosing using C using C cell number 4 and cell number 6 again. So you have 4 and 12 and 6 and 14. This construct a group of 4. Group of 4, which means here that you have A changing value, B is the one which should have B. You have also C changing value, C is out, and you have G is 0, which means you have what? You have B D bar. So the yellow group will give you B D bar, as you can see from this slide. At the end, you have the ones in red. The ones in red, you can take them as two groups, or you can have a group of what? Group of 8 here, because you have these 8 cells are considered as one group, because we mentioned before you have one cell, you have 2, you have 4, you have 8, you have 16. So actually you can use the for this rule, the 8 is a group of 8. And this group of 8, you can find that A and B are changing value. D changing value, you have only what? You have C bar. So actually this equation represents the optimum or optimized solution for your hardware. But actually it can be optimized more. If you take the D bar as a common, you will end up F equals C bar plus D bar multiplied by A bar plus B. So actually you are reducing the hardware again by 1 gate. This means that the KMAP will give you the optimized design, but sometimes you can use the equations in order to reduce it more, because here you have D bar as a common, so actually you can reduce your hardware by 1 gate by using the common factor. Again, if we go back to this slide, to this function, you can see that you have here what? 11 terms that you remember that if you are going with the standard solution, you have an equation f of a, b, c, d equal 11 terms, where you have to do it by hand and do it by equations in order to reduce the form from the huge number of terms into a simplified one. But here, as you can see from the KMAP, we ended up in no time. We got f equals c bar plus a bar d bar plus b d bar. This is the first example for the KMAP by using. Here we have another example for KMAP, where f is represented by polynomial of ABCD. So actually, as you can see here, f of ABCD equal a bar b bar c bar plus b bar c d bar plus a bar b c d bar plus a b bar c bar. As you can see from this expression, it's not the original one. Why not original? Because actually the original one should, each term should have all the total number of inputs. You have to have A and B and C and D represented in either in normal form or inverted form. But here you don't have that. You have three letters in one term, you have 4 letters in second term, and so on. So actually this is not the original. This is a reduced form from the original. So now we need to find where the position of ones in the A2 table or inside the KMAP. First of all, we have to go term by term. The first term here you have A bar, B bar, C bar. And we need to find where's the ones representing A bar, B bar, C bar. So the first thing we do is find where is A bar, B bar. A bar, B bar means the law which contains A equals 0 and B equals 0. So the first law is actually representing A bar, B bar, where A equals 0 and B equals 0. Okay, and now where's C bar? C bar will C equal to 0. So actually you have the first two columns representing C bar, which means that you have 2 vertical lines and 1 horizontal line. So the intersection between these 2 lines will give you the cell number where the ones exist. So as you can see here, for the term A bar, B bar, C bar, the cell number 0 and cell number 1 are the intersection between the horizontal and vertical lines, which means that you have the ones representing this term exist in cell number 0 and cell number 1. The second term, we have B bar, C, D bar. We do the same thing, the same scenario. C D bar is the last column because C equal to 1 and D equal to 0. And now we have where's B bar? B bar actually when B equal to 0, you'll find the first row and the last row will be equal to 0. So the intersection between these two horizontal lines with the vertical lines will be cell number 2 and cell number 10. So the ones in cell number 2 and cell number 10 represents the second term, which is B bar, C, D bar. The cell term is very easy because you have A bar B C D bar, which is actually is only representing one cell, where you have the second row A equal to 0 and B equal to 1, and the last row you have C D bar. So at the intersection between the horizontal and vertical line is cell number 6. So cell number 6, this is the one that represents the term A bar B C D bar. The last term A B bar C bar. A B bar is the last row where A equal to 0 and B equal to equal to 1 and B equal to 0, and you have C bar represented by the first two columns with C equal to 0. So as the intersection between the horizontal and vertical lines is actually cell number 8 and cell number 9. So the ones that are representing the term A B bar C bar is actually cell number 8 and cell number 9. Now what we did, we just mapped and we have just filled the positions of one inside the K-map by doing what we means the scenario we mentioned when we got system odds. Now let us solve the problem. The problem now, we need to find the maximum number of ones in a group. So the first group you can see is the four corners. As we mentioned before, the four corners are adjacent to each other based on the three-dimension plan. So actually what we have here, we have cell number 0, 2, 8, 10 are full group of 4. And as you can see, A is changing value, so A is out. You have B equal to 0, which means that you have B bar. You have C changing value, which means that C is out. And you have D equals 0, which means that you have D bar. So the value for this group will be B bar, D bar. The second group, the second maximum number of ones in a group, you find the red group here. The red group was cell number 0, cell number 1, cell number 8, cell number 9, representing group of 4. And as you can see, again, A changing values, A is out. You have B equals 0, which means you have B bar. You have C equal 0, which means you have C bar. You have D changing value, which means D is out, so the term will be B bar, C bar. The last term here, we have 1 in cell number 6. The one is better not to take 1 by itself. You have to find a group. So you can have a group of A group of 2 in cell number 2 and cell number 6. So actually this term is representing what? Is A equal to 0. You have B changing value for B is out. You have C equal to 1 and D equal to 0, which means that you have A bar, C, D bar. This is the solution for this example, and this example can be reduced more by using equations. If we take B bar as a common factor, you find that F equal B bar multiplied by D bar, B bar multiplied by D bar plus C bar, or plus mean A bar C D bar, and this will be a reduced function for your example. In this slide, we are going to define a certain definition for the K-map, what's called prime implicant. A prime implicant is a product term obtained by combining the maximum possible number of adjacent squares in the map, which means any groups or maximum group of ones or maximum groups of zeros. The term that comes out from it is called prime implicant. So this is actually the outcome from the K-map. A prime implicant might be essential or not essential. Essential means that you have to take it, there's no other choice. But non-essential, you might have a choice of either two alternative solutions, or you might exclude the system from your equation. So actually, you're going to see from the next examples what's meant by essential prime implicant and non-essential prime implicant. In this example here, we are going to show you what's meant by essential and non-essential terms. Actually, if you see here, you have 1 in cell number 1, cell number 3, cell number 4, cell number 5, cell number 6. Let me first of all find out what will be the maximum number of ones in a group, and also what will be the outcome from this K-map as equation. The first group here is cell number 1 and cell number 3. You have a group of 2. And this group, actually, we can say is essential. Yes, it is essential. Why? Because cell number 3 has no other choice rather than combine with cell number 1. So the group of 3 and 1 is essential A group, and the result from this group will be X bar Z. The second group here is cell number 6 and cell number 4. Notice that cell number 6 has no other choice other than combine with cell number 4 to give you a group of 2. So actually cell number 6 and 4 are essential, and this cell will give you, and this group will give you X Z bar. Now we have cell number 5 where it exists one here. you have two choices, either to take 5 with 4 as a group of 2, or 5 with cell noun as a group A of 2. So actually here you have two solutions. The first solution, if you take 5 and 4 as a group, you'll end up with xy bar. But if you take 5 with 1 as a group, you will take a y bar. Here you have two equations representing the same function, where either f equal x bar z plus xz bar plus xy bar, or f equal x bar z plus xz bar plus a y bar z. This is actually two solutions for the same same function. So actually this is what you call it as a non-essential solution, because here you have two alternatives. You have to take either one of them, the first equation or the second equation, but they are equal to each other. So what you can say here, x bar z and xz bar are essential prime implicants, while xy bar and y bar z are non-essential prime implicants. This example gives you an idea what's meant by essential and non-essential prime implicant. Here we have another example also for the essential prime implicant, non-essential prime implicants. Actually, we have ones where in cell number 1, number 3, 4, 5, 7, 6, 12, and 14. First of all, you need to find out, you have to solve, if you're going to solve this problem, you have to find where are your essential groups, and then you find after that where is your not essential groups. The first one here, you have cell number 6 and 14 and 4 and 12. This is group of 4, and actually as you can see, this is essential because you have no other choice rather than taking this group of 4, because 14 and 12, they have no choices other than combining with 6 and 4. So actually what you have here, this group here is essential, and will give you a B bar. And the other one here, we have 1, 3, and 4, and 5, and 7. This group of 4 again, and this group of 4 also you have is essential, because cell number 1 and 3, they have no other choice rather than combining with 5 and 7. So actually this term will give you a bar D. Okay, now what we have here, we have is this group. This group here is from 4 and 5 and 6 and 6 and 7. This group is group of 4, but actually all the ones already we used before. This is what we call that you get a bar B, but actually this is essential and this is non-essential. But non-essential means what? Do you need it? No, of course not, because already all ones exist in the first two terms. So f equal a bar d plus b d bar. This is essential, and the a bar b is not essential and it's not required because it's redundant. And if you remember the consistency theorem we mentioned before in one of our lectures, consistency theorem says what? If you have a d bar, a bar d plus b d bar, actually as you can see here, a bar b is redundant, and this is actually comply with the consistency theorem, because you have d exists with a bar, d bar exists with b. So what you, if you have a bar b as a term, this term can be excluded from your equation, and we have a proof of that when we talked about the consistency theorem. So actually the function here b at the end, f equal a bar d plus b d bar. So we took only the essential, and the non-essential we can take it out from our equations, and this is what happened in this example. Here's another example also for the essential non-essential groups. As I mentioned before, you have to look first for the essential groups, and then you look for the non-essential prime implicants. So let me first start with this equation here. This is equation represents the function. As you can see, the first group here, or the first one we have in cell 0. Cell 0 is nothing adjacent to it, so we have only 1 inside cell 0. No one can tell me that 0 is adjacent to 10, because you don't go diagonal. 0 should be adjacent to number 2 or number 8, but this is not the case now. So actually we have cell number 0. It's representing the first term, which is a bar, b bar, c bar, d bar. This will be essential a prime implicant, the first one. The second group here, you have this one is essential too, because 5 have no other choice rather than combining with cell 13. So actually this group will give you B, C bar D. And also this group here is also essential, because 12 has no other choice rather than combining with a group of 2 with 13. So we'll end up with A, B, C bar. And also this group here is essential because 10 has no other alternative other than taking 11 as a group of 2, and you end up with A, B bar, C. Now we have 1 in 15. 1 in 15 you have two choices. Either you go 15 and 13, and this will give you the term ABD, all you have 15 and 11, which would give you the second term was ACD. So actually these are not essential. So actually we have now two equations representing the same function. One which includes ACD and the other one that includes ABD. So actually we have two solutions for the same function, but here we have a redundant, actually alternative solution for F. So this is an example also for the essential and non-essential groups. In this slide, we are going to talk about the complement of a function with f bar. As you mentioned before in the previous lectures, if you want to get f bar, you have three different ways to get it. One, by using the truth table. If you are looking for ones, you are getting f. If you are looking for zeros, you are getting f bar. If you are talking about the sum of product. If you're talking from the point of view of product of sum, if you're talking about zeros, taking the zeros, you will get f, and if you're talking about f bar, you will take the ones. So actually here, the complement function can be obtained also from the truth table. If you are getting sum of product, the group of ones will give you f, and groups of zeros will give you f bar. If you are talking about product of sum, the group of zeros will give you f, and group of ones will give you a f bar. In this slide, as you can see, we have a product of sum, and if you take for product sum f equal f double bar equal f, which means if you take the double inverting for the same for the function, you will end up with f. This example also shows you that f double bar equal f, and we're going to see this in the next example what's meant by that. I'm going to give you that f, the K-map gives you f as a product of sum, f bar as a product of sum, f as a sum of product, f bar as a product of sum. As you can see here, the example we are giving is f of a, b, c, d equal sigma 0, 1, 2, 5, 8, 9, 10. These are the positions where f equal to 1. The other numbers of the cells, yeah, will contain 0. So actually what you are going to do here, we need to find what's f bar as a sum of products. Sum of product means 1 is true and 0 is false. The first group here, what we have, group of 4, in cells 3, 4, 3, 7, 15, 11. Actually this group contains the maximum number of zeros, not ones, which means that you are getting now f bar. So this group gives you c, d bar. The second group here, this one will give you what? Will give you A, B. So actually what we have here, you have A, B. And the fourth group, which is one between this 4 and 6 and 12 and 14, this will give you B, D bar. So actually F bar, because as long as these are groups of zeros and we are talking about some product, F bar equal AB plus CD plus BD bar. Now I want to represent the same groups here as a product of sum. Product of sum, if you talk about it, you will find it out equal what? If you find this will equal a bar plus b bar multiplied by c bar plus d bar multiplied by b bar plus d, because actually when you are talking about product of sum, you have 1 is false and 0 is true, and this will end up with f. So if you go to the left hand side, you find if I'm taking f bar equal ab plus cd plus bd bar, if I take the dual of f bar, I will end up with a f bar equal a dual of f bar equal a plus b multiplied by c plus b multiplied by b plus d bar. And if you complement each letter, which are taking f double bar, which will end up with f, will end up with what? F as a product of sum, as is shown here. F equal a bar plus b bar multiplied by c bar plus d bar multiplied by b bar plus d. So actually, as you can see here, whether you are doing it by the procedure of getting f double bar from the duality function, or you are getting the groups of zeros. When you talk about the group of zeros as product of sum, you will end with f bar. When you are talking about a group of zeros as a product of sum, you end up with f. Let me define here another definition in the K-map. We have something called don't care. Don't care terms, there are applications where the function is not specified for certain combinations of variables. Do you remember the BCD code? The BCD code, we said what? We have BCD code because it's actually 4 digits, but 4 digits you have to go from 0 up to 15. But what we did with BCD, we are defining only the decimal numbers, which are 10. So we are taking 10 out of what? 10 out of 16, which means you have always 6 undefined states. 6 undefined states, this is what you call the don't care terms. So actually this very example here is an example talking about BCD, talking about XS3, talking about 2 4 to 1, talking about 8 4 minus 2 minus 1. All these you have full 16 combination. You are using only 10 out of 16, which means always you will have 6 undefined states. So this is what we call the unspecified minimum terms are called minimum term, and can be used on a map to provide further simplification of the function by considering it as 1 or 0. We're talking about a, depending on the situation, of course, you can define these cells which are unspecified as 0 or 1 as you wish. So actually this is what we call a joker of the K-map. Joker means you can use it by any value you want if it is it will help you reduce your hardware. So don't care terms is as always represented by a cross. A cross in the map means that you have here don't care. This don't care you can use it either 0 or 1 based on your choice. So actually this is another reduction for the K-map, and the same what we call it the joker of the K-map. In this example, I'm going to give you an idea about how to use the K-map, also the don't care. The don't care inside the K-map are representing by x. Actually, if you can see here, you have x in 0 and 2 and 5, which means that you can define the function f in two terms. One, f equals sigma m of 1, 3, 7, 11, 15, where the 1 exists. And the second one will be d equals sigma m of 0 and 2 and 5, which means these are the positions where the x's are, or the don't care exists. So actually you have two definitions of function f. One where the ones and the other one where is you don't care. So if you do that, you will find that the function is actually what you want looking for is the ones in cell 1, 3, 7, 11, and 15. In order to do that, you are going to, from the K-map, to find out what f is equal to. Now we have to find the group of 4. The group of 4 here, as it shows here, you have CD. CD is common for the function. This is the main part of your function. F will f equal 1, 1, 1 in cells 3, 7, 11, 15. So you have here the term CD represents that group. Also, we still have 1 in cell number 1. You can have cell number 1 by itself, or you can have cell number 1 with cell 3 in group of 2, or you can make use of the joker of the A that don't care. If you want to make use of the joker of the don't care, you can have two choices. The first choice for F2, if you have this group of 5, if you include 5 in your group and you say that the don't care is 1 here, you have the chance, or you have the advantage of taking the don't care either 1 or 0 based on your choice. So here in this example now, I have choose that cell number 0 you have 0, cell number 2 you have 0, and cell number 5 you have 1. So now we have, with the 1 in the 5, you have a group of 4 between 1, 3, 5, 7. 1, 3, 5, 7 represent a group of 4, which is equal to A bar D. So this is actually F2 equal CD plus A bar D. Where is my F? My F actually exists because it's embedded inside F2, because F where F is equal 1 in cell number 3 and 1 and 3 and 7 and 11 and 15. So actually your F is included inside F2, but F2 you have included also you don't care in 5 equal to 1. Another choice or another example, another solution, if you want to do it, you will have the group of the second function where you have cell number 0 you have 1, cell number 2 you have 1, and cell number 5 you have 0. In this example here, you have another function called f1. F1 equal what? Equal CD, which is we have it before, plus A bar B bar. This means that you have two definitions for your function. Function f1 where x the don't care inside the map. In 0 you choose x equal to 1, 2 you choose x equal to 1, 5 you choose x equal to 0. So you ended up with f1 equal cd plus A bar D. While in the other solution you made a choice of 0. In cell 0 you have x equal to 0, in cell 2 you have x equal to 0, in cell 5 you have x equal to 1. So you ended up with f2 equal cd plus A bar D, which means that f1 does not equal f2. But where is my f? My f actually is embedded inside the two functions. So f1 f for my f is inside f1, my f is inside f2, but f1 does not equal f2, because in f2 you have a situation where in cell 5 you have 1, in cell 0 you have 0, in cell 2 you have 0, while f1 you have in cell 5 you have 0, and cell 0 you have 1, cell 2 you have 1. So actually these are two different solutions for f, but actually f is inside both of them. So both are true, both are correct, but you have an optimized solution, but again f1 does not equal f2. Okay, so as you can see that what's written here in this slide, he said algebraically these two functions are not equal, as both covers different don't care minimum terms, but the original function is satisfied, as don't care terms will not affect the original function. And this is example of how to use the K-map. And here I can give you an exercise to do it at home. You need to do a converter or decoder or encoder, which means you need to transfer BCD to XS3, XS3 to 241, 241 to 841 and so on. So you can do this exercise by adding now from cell number 10 to cell number 15 for the BCD as don't care, or any undefined states you have it and don't care. So you have an exercise at home to do whatever conversion is for decoder, encoder, and converter. Do that at home and let me know what you ended up. Thank you. We have been solving the K-map with 4 variable K-map. If you have more than 4 variables, this means what? This means if you have 5 variable map, you need 32 cells. If you have 6 variable map, you have 64 cells. So in order to follow the rule of changing only one value, one digit per, if you go to any adjacent vertical or horizontal cells, it will be very hard for you to work with 32 cell and then 64 and so on and so on. So in general, maps with 6 or more variables need too many cells, and they are impractical to be analyzed manually. So we have to use a computer simulation program in order to handle such situations. So actually, in by hand, you can solve up to 5 variable K-map. After that, you have to use a computer simulation. In this slide, we are going to discuss what you should do with the 5 variable maps. If you want to see what's going to happen with the 5 variable maps, you have to understand what it looks like. First of all, let us study the table giving here on your right hand side. You have the 5 variables A, B, C, D, and A, B, C, D are constructed like that. E is the least significant and A is the most significant. E, you have for column E, you have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. For column D, you have double zeros, double ones, double zeros, double ones, double zeros, double ones. And for the C, you have 4 zeros and 4 ones, 4 zeros and 4 ones. And for the B, you have 8 zeros, 8 ones, 8 zeros, 8 ones, and so on. And for the A, you have 16 zero and 16 A. Actually, what we're going to do here, we are going to split this table into 2 layers, upper layer and lower layer. The upper layer actually you have A equal to 0, 16, 0, and the lower layer you have A equal to 1, you have 16, 1. So actually you have 2 layers, one with A equal to 0 and the other layer with A equal to 1. And this is what is written here. We use four variable maps. So actually we are going to divide, instead of having 32 cell and the map of 32 cell, we're going to divide it into 4 variable maps. And why is that? Because if we are going to deal with the 32 cell inside the map, it will be very hard to manipulate the rows and columns in order to meet the rule that says that you have only one digit changing value from one cell to adjacent one, so even either it is horizontal or vertical. So this will be too hard to follow and too hard to implement. That's why we divided the cells. Instead of having 32 cells, we are going to have 4 variable maps, on one with A equal to 0 and the other one with A equal to 1. If you think about it, the layer 1 and layer 2, the upper layer and lower layer, this means that if you see the tables at the end, at the below here in this slide, you can say the A level or A0, A70, A equals 0 maps is on top of the A equal 1 map. So this means what? This means that cell number 0 is adjacent to cell number 16, cell number 1 adjacent to cell number 17, and so on. So actually, as if you are taking this map, putting it on top of the other one. So this is what we call bridging, or this is what we call layer 1 and layer 2. So as you can see here, M4 is adjacent to M20, M15 adjacent to M31. So actually you can understand that the adjacency now is not only horizontal or vertical, it's going in direction a 3-dimension. Actually you are going to something called bridge, or something called you have layer 1 and layer 2, so which means that it's cell on top of each other. And as you can see here, that what, as I mentioned before, if you have a group in A, you will have only group that's satisfying as a layer A, another group satisfying layer A equals 1 equals 0, and you have also something common between the two maps. So this will kind of explain more with the next example. But let me understand now that you understand the situation. The situation now, what we did, you have divided the 32 cells into two full variable cells, and you have two layers. Layer 1 with A equal to 0, and layer 2 A equal to 1. This slide here just is repeating the same thing. I'm doing 5 variable maps, so we have two maps, one is equal to 0, one equal to 1, and next we're going to give you example now how to deal with such a situation. In this slide, we are going to solve for five variable maps. Actually, as we mentioned before, we are going to divide it into two full variable maps, and one with layer A equal to 0, and the other one with layer A equal to 1. Here, if you see that f of A, B, C, D, E equals sigma m of 0, 2, 4, 6, 9, 13, 21, 23, 25, 29, 31. This is a position where f equal to 1. We are going to put the ones in their place inside the two maps and then try to find out the solution. Notice that we have layer 1 with A equal to 0 and layer 2 with A equal to 1. So you have to understand, if you have a group that associated only with A equal to 0 and have nothing to do with A equal to 1, this means that any term will come from this layer should have a bar in common with the terms. If you are talking about any group is associated with only A equal to 1 layer, this means that any parameter or any term that comes out from this layer will be also associated with A in the equation. And if you have a group that is common between the two layers, layer 0 and layer 1, you should understand that A now is changing value, so you have to exclude it from your equation. So now let us solve the problem. The first group that we have here is this group. This group here, we have the cells only 0 and 4 and 2 and 6. These are the four ones inside the one group of 4. And as you can see, this group has nothing to do with layer 2, which is equal to 1. This means that this term here will come with a certain value, but you should have a bar associated with it. So actually, as you can see here, this term will give you what will give you B bar, E bar. B bar, E bar, and should have what with it to have A bar with it. So the term will be A bar, B bar, E bar. The second group here, which is this between cell number 21 and 23 and 29 and 31. As you can see here, this is a group of 4 and it has nothing to do with layer 0 map, and this means that this one here that you have to have A as common, because this map is associated with A equal to 1. So actually this term here will give you what? Will give you CE, and you have to write A with it because the term will be ACA, because A is common here for any term that comes out from this layer. Now this group here, as you can see, is common between the two layers. It's 13, 19, and 29, and 28, and 25. So actually, as you can see here, this is A is changing value because the group now is common between the two layers. So this means A equal to 0 and A equal to 1 are involved, and this means that we don't have to write A anymore, and actually will be the solution of this group will be common, which is called B D bar E. And actually, if you can find the solution, F equal A bar B bar E bar plus B D bar E plus ACE, and this is what's meant by dividing the 32 cell into two four cells and four variable cell. And this is the solution of this example. I hope you understand what's meant by solving 5 variable. Thank you. Assume if you don't have any gates in any type of hardware, except you have inverter, you have switch, you have power supply, you have a LED. So how can you build any gate by using these four components? I mean inverter, I mean power supply, I mean LED, and a switch. The switch, we have two types of switch. One is manual and the other one is electronic. The manual one is a normal switch which have you by your finger to a on off on off on off. While the electronic switch is controlled by a control input. So actually we are going to talk in this slide about what's meant by transmission gates. Transmission gates, this is available with CMOS type electronic circuits, and actually, as you can see from the symbol, it has control C and C bar. Control C and C bars, you do the same function except the C. Whenever C is 1, C bar is 0. Whenever C is 0, C bar is 1. And you are using this to control signals in order to control the circuit. So actually, if C is working fine, you can use it. If C is not working, you can use C bar and vice versa. So they are alternative to each other, but actually C and C bar are your control inputs. And also you have here input X and input Y. Input X and Y, whenever you have C equal to 1 and C bar equal to 0, this means that this is a source circuit, so this means pass signal. Pass signal, which means X equal to Y. Whenever you have C equal to 0 and C bar equal to 1, this means an open circuit. Open circuit means there is no relation between X and Y. So actually, when you say C equal to 1, it's a short circuit. When you say C equal to 0, it's an open circuit. So actually, we are going to use this type of a switch in order to build all the gates that you have used before, which means the XOR, the XNOR, NAND, the NOR, whatever. So actually, we can use this type of full components, the transmission gate and inverter and power supply, and you have the LED. So these four components, you're going to build all the necessary gates, as you're going to see in the next slide. In this slide, I'm going to give you an idea how to build an XOR. XOR, before building it, you have to draw the truth table of XOR. The truth table of XOR is shown here. You have X and Y and X and output Z. You have Y0101, you have X0011, which means this is your input and your output will be 0110. Why is that? Because the property of the XOR, whenever you have an odd number of ones, you will get 1. Whenever you have even number of ones, you get 0. So this is actually the function of the XOR, and as written in the equation, Z equal X XOR Y, which means equal XY bar plus X bar Y. Okay, now I need to build this one with the switches. I have to decide how many switches do I have, or do I need to use. If you see here, you have to decide, assign which one is your input, which one is your output, and which one is your control. So I have decided here to have the leftmost X as my control. X is control means I have X0011. This will divide the truth table into two parts, upper part and the lower part. The upper part is controlled by X equal to 0, and the lower part is controlled by X equal to 1. Okay. Now I have decided, I have assigned X to be my control for the transmission gate. I control the transmission gate, as I mentioned before, it has C and C bar. Now I'm talking about C. As AC, it will be your control now. So I have to make sure whenever X equal to C equal to 1, you have a short circuit. When C equal to 0, you have a open circuit. So I have now to decide how to build my circuit. Let me now talk about the upper part. Whenever C equal to 0, what is the relationship between Y and Z? As you can see here, Y equals Z for the upper part. Y equals Z, which means for the first transmission gate TG1, you have input Y and you have output Z. So actually you have to enter Y to the TG1. And now we're going to analyze the second is the lower part. The lower part, whenever X equal to 1, you have to have a Z, the relationship between Z and Y, Z equal Y bar. So actually for the second switch, TG2, you have to enter Y bar. So now I have two switches, TG1 and TG2. The first switch, TG1, have input is Y and output is Z. The second switch, TG2, you have Y bar as an input and you have X as your output. Now I have two switches. I have to make sure that whenever the one of them is open at the time and the other one is open circuit, so I have to make sure they are not open at the same time. So actually I have to make sure of that. So let me see and analyze the table. So whenever X equal to 0, I have to make sure that TG1 is closed and TG2 is open. To do that, I have used the inverter in order whenever X equal to 0, as you can see in the diagram here, X equal to 0, this means that the control of TG1 is 1, which means TG1 is short circuit and TG2 is a open circuit. So when X equal to 0, TG1 closed and TG2 open, which means that TG1 closed, it means that Z equal to Y, and this satisfies the upper part of your truth table. The second one, whenever X equal to 1, you find that TG1 is open circuit and TG2 is closed circuit, so this means that Z equal Y bar, and this satisfies the equation of that XOR, and this is how we built the XOR gate. Now I need you at home to do the same scenario, the same exercise to do it for all other gates. You have to build an AND gate, OR gate, XOR, NOR, NAND, whatever. So I need you to do the same scenario to build your circuits, and this is how to use the switches in order. If you don't have any gates in your lab, any gates anywhere, you can use is a full components TG transmission gates, and using an inverter and using power supply and LED, you can build whatever gates you are looking for, and this is an exercise for you to do at home for the other gates. Actually, this slide and the coming ones will be theoretical, but you have to understand it and to keep it in mind, because this is the key about the design, about our knowledge for the integrated circuits, for the functionality, for the technology, and so on. So first of all, we have to understand what's meant by integrated circuit. IC integrated circuit, which means a دوائر متكاملة, which means that you have to have a function. You cannot work without a defined function. It is a small silicon semiconductor crystal, of course crystal, because we have to organize the atoms in a way in order to control them. You cannot get it from the land, because the silicon itself, when you get it from the sand, it's actually the atoms are not distributed inside. They are scattered everywhere, so whenever you have a voltage difference, it will go anywhere and it will be collision. That's why we have to have a crystal. Crystal means we are organizing the atoms in a way to control them, in a way like a cubic organization or whatever. So actually this is a way to control, in order if you have a certain voltage difference, or voltage difference between 2 points, it will go in a certain direction, which will give you positive current or negative current. Actually, this crystal contains the electronic components of your digital gates, so it's a resistor, capacitor, and so on. The number of pins, because as you can see, the integrated circuits, they have a certain number of pins, starts from 14 and goes to 64, 128, and more. So actually, the number of pins you have, the more pins you have, the more a control you have on your chip, because this is a relationship between you and the circuit inside your IC. So actually what you see from the IC is its legs. The legs are assigned to a certain input, certain output, VCC, ground, whatever, a clock, and whatever the input is. But this is actually the outsider, so actually are controlling the inside of the chip by this pins. So the more pins you have, the more control you can do. But the less pins, you have a limited number of pins. This means that it's not that possible to control the IC inside. So actually, the pins only assigned to you for you to understand how to enter the input, how to get the output, how to have a VCC and ground connected, how to have a clock, and everything like that. So this is the starting point of is understanding what's meant by IC. When you talk about integrated circuits, we have several levels of integration. What you have in the lab so far, we dealt with small scale integration and medium scale integration. Let us describe here what is meant by small scale, medium scale, large scale, and so on. The levels of integration depends upon the number of gates and the accessibility from the pins to your input A devices, components I mean. In the small scale integration, SSI, the number of gates is less than 10, and the inputs and outputs are connected directly to the pin. As you can see for the AND and OR and this inverter and so on, you can see that the ICs you connected directly. You know pin number 1, pin number 2 are inputs, pin number 3 is your output, and so on. So you know exactly where is your input and where is your output, and this is actually if you have inside the IC, you will find that the number of gates is less than 10. Okay, and the relation is directly between in and out and the end user. For the small medium scale integration MSI, you have from 10 to 100 gates, and this is for decoder, adders, register, and so on. So as you can see, there's some inputs you have direct relation with, and some inputs are inside the circuit itself, but you can control. Actually, this small scale integration I'm talking about from 10 to 100 gates. For the large scale integration circuit LSI, we have from 100 to few thousands of gates, and this is like processors, memory chips, and programmable modules. And you can see it's very difficult to have all the inputs assigned to the output pin. Well, actually, you assign something to the output pin, and then you have intermediate inputs inside until to reach the function you're looking for. So actually, it's so hard to go through inside the IC itself, because what you have control on, you have control on the outside pins, not inside of the chip, but you can control by a certain scenario or certain inputs. You are controlling whatever inside your hardware for the large scale. For very large scale integration circuits, we have thousands of gates, and thousands of gates means a large memory array, complex microprocessors, and so on. And we have also the ultra large scale circuits can go to billions of gates inside the same IC. You can build the system and do whatever. So actually these are the level of integration, and as you can see here, it depends upon the number of gates inside and the accessibility from the end user to the inside of the chip itself. This is actually what we call a different levels. In the next slide, we're going to give you the different technologies. As long as we have level of integration, we have also different types of technologies used for integrated circuits. We have what's called DTL, digital logic families. We have DTL, TTL, ECL, MOS, and CMOS. Yeah. The DTL, actually we're talking about in the circuit, you have the diodes and transistor to build the configuration of an AND and OR and so on. For the TTL, as you can see here, we have what's called transistor logic. It's actually the diodes and transistors also, but the power supply here is 5 volts, and the two logic levels, logic 0 and 3.5, and this is actually standard, but the problem is the TTL is huge. That's why we use it only for small and medium scale integration. For the ECL, if you need a metal coupled logic, it's for high speed operation for supercomputers and signal processors. This means that if you need something that needs high speed and needs graphics and images and so on, you use what's called, the technology is used here is ECL. It is like the TTL, but it's more expensive than the TTL. That's why it's not you can find it in memories, you can find it in supercomputers, you can find it in devices that deals with signal processing. If you need a small size of a transistor, the MOS is the right one. It is actually metal oxide semiconductor. It is high component density because it's very small in size, and it's a simple processing techniques during the fabrication. So actually, it's easier to fabricate, and it has a very small size, and you can use it for large scale integration, ultra scale integration, so on. That's why nowadays we are using the MOS because of the size and the power consumption and the ease of fabricating it. We have also the CMOS. The CMOS is a complementary metal oxide semiconductor. It is actually two devices in one. We have two MOS. One of them is NMOS, so the other one is MOS, because the MOS is a unipolar device. Unipolar means it has only one carrier at a time. That's why the CMOS uses two carriers. I didn't mention for you the TTL, the bipolar transistor is used for TTL. The bipolar actually uses two carriers in order to carry your data, and actually it's very fast because you have two carriers inside. But as MOS, it has only one carrier because that's why it is called unipolar, because it has only a carrier. We have NMOS and PMOS. The CMOS is actually combining the NMOS and PMOS in one device called the CMOS, and this is has a very low power consumption, and the speed is a little bit moderate than the MOS itself. So it's actually something between MOS and the bipolar transistors, and these are the digital logic families used in order to build whatever technology is for NAND, NOR, whatever functionality is. Actually, this note for you to understand that there are many types of TTL families. We have the high-speed TTL, low power TTL, Schottky TTL, low power Schottky TTL, advanced low power Schottky TTL, and so on. And the ECL gates operate in nano saturated state conditions that allow the achievement of propagation delay of 1 to 2 seconds. Actually, this is because of the speed, of course. This is gonna be learned when you take the microelectronics subject. Not here. I'm not going into details here because here we are dealing with digital circuit. But actually, this is for your information to understand, and you get more details about it when you go to the electronics course. In this slide, actually, we are going to talk about some important parameters that are evaluated and compared if you are doing hardware. How can you evaluate your work? First of all, we're talking about fan out, we're talking about power dissipation, we'll talk about propagation delay and noise margin. What is a fan out? Fan out actually, if you are having some output and you want to distribute this output among more stages. I mean, you want to feed other gates, not only one but more than one. As if you have here at home, you have the electricity outlet from the wall, and this electricity outlet sometimes you use what's called the electrical distributor unit, which is اللي هي المشترك يعني. The electrical distributor unit, what it does, it actually, you can with this one outlet you can feed more than one device in order to have it all of them working not at the same time but working from the same outlet. So actually, if you do that, if you remember the Kirchhoff current law and Kirchhoff voltage law, there's some limitation. You cannot put, say, 5 devices or 6 devices or 10 devices from one A1 out, because something is called load. The load equal the power equal voltage multiplied by current. So if you have one outlet, this means, if you are in series, this means that you have the same current, but you have different voltage, V1 and V2 and V3 and so on. So this means you cannot operate all the devices at the same time, because the device, if for the device to operate, we have to have the power that is enough in order to operate this device, which means you need V multiplied by I equal a certain amount that is capable of starting your device. So sometimes if you have different devices in series, this means V1 multiplied by I1, then V2 multiplied by I2, then V3 multiplied by I3, and so on. Sometimes the voltage multiplied by current will give you a power which is not enough to operate the fifth or sixth device. So actually, this is what is meant by fan out. The maximum number for the digital system in order to feed a different gates after from one output is actually 8 gates. You can feed 8 gates, and then you can use a buffer in order to delay the signal from going to the third one for the other units and so on. So actually, here's a fan out for you is actually one of the main parameters you have to measure and you have to make sure of. The power dissipation, of course, you need the power to be minimum as possible. The propagation delay, you need the propagation delay to be minimum as possible. And the noise margin, you have to have a certain margin for noise in order to not to disturb two machines working side to side. So actually, the noise margin is very important because it might disturb the performance of your device. So it needs a noise margin to be enough in order to accept some certain percentage of noise in order for your device to operate properly. Actually, this slide and what comes next, we're describing what I mentioned in the previous slide about the fan out, the power dissipation, and noise margin, and delay. Actually, the fan out described here, it specifies a number of standard loads that the output of a typical gate can drive without impairing its normal operation. And the standard load is usually defined as the amount of current needed by an input of another similar gate of the same family. So this is actually what's meant as fan out, and I described it in my previous slide. This one also describes what's meant by power dissipation. The power dissipation, it is the power consumed by the gate which must be available from the power supply. Then the propagation delay. The propagation delay, it is the average transition delay time for the signal to propagate from input to output. When the binary changes its value, the operating speed is inversely proportional to the propagation delay. And the last one is the noise margin. Noise margin, it is the maximum the maximum external noise voltage that cause an undesirable change in the circuit output. This is actually a brief description of these parameters, which are very important for us to evaluate. In this slide, as long as in math we have positive signal and negative signal, here also in logic we have positive logic and negative logic. When we choose a high level H to represent logic 1, it defines a positive A logic system. L to represent logic 1, it defines a negative logic system. So as you can see here in this figure, if 1 is high and 0 is low, this is called positive logic. When 0 is high and 1 is low, it is considered as if as if you have a negative logic. So based on that, you have to have this important note here. In any data sheet for any component, you'll find H and L. So the signal values H and L are usually used in the component's data sheet. The actual truth table is defined according to the definition of H and L in the data sheet. This is what you're going to see in the next slide. In this slide, you're going to see the data sheet. You have X and Y and Z. X and Y input, Z and output. You can find you are using here L and H. L and H, which means that it's low and high, but actually if you're talking about positive H, is talking about H is 1 and L is 0, as you can see in the left-hand side. This is actually describing an AND gate. So whenever you substitute L 0 and H1, you find it's an AND gate. If you are talking about negative H trigger, negative H, negative logic, you find that L is 1 and H is 0. If you do that, you find out that this corresponds to an OR gate. But OR gate here, as you can see, the table on the right hand side is not correct. I made it on purpose in order for you to understand this is an OR gate, but actually the actual we are substituting L is 1 and H is 0. L is 1 and H is 0. So this table is not correct. This table on purpose I did it like that in order for you to understand this is an OR gate. And as you can see here is a symbol. If you need to differentiate between positive logic and negative logic, you find that the AND gate is normal, but the OR gate here you can find a triangle in front of the inputs and the outputs. So if you see any symbol with a triangle in the inputs and the outputs, this means these people are working with negative logic. And if you can see that triangle, it is actually a normal AND gate is actually to be a positive logic system. Okay. In this slide, we are going to talk about logic circuit at large, which means the logic circuit is divided into two categories. One is called combinational and the other one is called sequential. The combinational is what we had before and we will have in our lectures in the first part of the subject. And actually, if you see the upper right corner, you can see we have two configurations. One with two NAND, both of them composed of two NAND gates. The left one, you have two NAND gates, but you have four inputs A, B, C, D, and you have two outputs. This is the combinational part. The combinational part here, as you can see, if A, B, C, D are known, the outputs A, you can detect what the output A will be at a certain time. So actually, we can say that the combinational circuit consists of logic gates whose output at any time the present input. Present input means it's a relationship between input and output, and which what we called before the truth table. The truth table is a relation between in and out. As you can see from this configuration here, we have no feedback. All storage are involved. So no feedback or storage involved in combinational because it does not relate upon dynamic current at the time, but it is upon a certain time you get a certain value, and this value will not change as long as the inputs are the same. So actually combinational, if you know the inputs, the output is known at a certain time. So this is no feedback. There is no storage elements, nothing at all involved in a combination. When you talk about sequentials, this is the right hand side configuration. You can see we have the same two NAND gates, but we have two inputs here, S and R, and you can see that the output is fed back again into the NAND. This means we have a loop. This loop will give you a problem because you will never ever know what is the operation of this circuit unless you have a previous information about the inputs, the previous inputs, which is in this time, which is historical data, or you can initiate initial value. Initial value or initiating initial value or finding out what is the previous value of the output. This means there is a relation between this circuit depends upon time, which means as long as it depends upon time, it depends upon a frequency, because we know the frequency f equal 1 over t. So here is some relation between time and the operation of your circuit. Otherwise, the circuit will not operate. You have to have either initial state or you have to have what's called the previous value of your state. The previous state, I mean. So actually, what you can say here is that the sequential circuit involves storage elements, and we call it flip-flops. Flip-flops from the wording, it means something going up and down, up and down, up and down. But as long as we are talking about digital signals, we are talking about two values, so we are talking about a square wave. A square wave, why? Because a square wave, it goes from 0 to 1, 1 to 0, 0 to 1, 1 to 0. So actually you have to have a square wave. This is called the time sequence. The time sequence here, which means that the circuit depends upon time, and as long as depends upon time, it depends upon a frequency, and this we're going to learn in the second part of your course. So what we can say here, the sequential circuit, it involves storage element flip-flops. Actually, the output here is not only a function of inputs. As you can see, outputs are a function of inputs and the state of the storage state. So actually it depends upon two values, the inputs you are entering and the state of the storage element, because this is a depending on time. So actually what's meant by the state of the storage element, where the state of the storage element is a function of the previous input. This means you have to have a previous value from the input in order for this loop to go on and go on and go on. That's why here we are saying we have present state and we have something called next state. Like a counter, you have a counter can do what? It counts from 0 up to 1. So your present state is 0 and next state is 1. And then the 1 will be present and the 2 will be next. You go from 1 to 2 and then from 2 to 3 and so on. So one of them is present and the other one is next and so on. So this is mean they are a certain time you are depending upon the value at this time. So here the state of the storage element is a function of the previous input, because 0 goes to 1 and then 1 goes to 2 and so on. So actually it's always a function of a previous input. So that's why I'm saying here outputs are functions of inputs and the state of the storage element. At the same time, the circuit behavior must be specified by time sequence of inputs and internal states. You have to have a time sequence in order to know at a certain time what is happening at this time and what will happen next time and so on. So we have present state and next state, as you can see when we describe the sequential circuit in our second part of the course. This slide here shows you graphic illustration for what I mentioned in our previous slide. Here, as you can see, that you have this logic circuit divided into combinational and sequential. As you can see from the graph here, a combinational circuit, you have the n inputs and you have m outputs. So as long as the n inputs are known, the outputs are known. And actually, this is a sketch of the combination. If you talk about sequential, you can see the feedback. As you can see, you have the same block of the combinational circuit which does the function. You have the same inputs, the same outputs, but now part of the output or partial output next, which is called next state, will go into storage element. The storage element will go back again. It will be called present, because present is what you have in your hand. Next is what's going to happen after going inside the combinational, and the storage will be the part which will decide when you can receive the next state to be changed from next to present. And this is how the sequential circuit will work, and we're going to understand this more when we talk about sequential in the next part, the second part of the course. So here you can see the difference, that the outputs is a function of inputs and present state, and you can see that the next state is a function of inputs and present state, while in the combinational the output is a function of inputs only. So here you can see the difference between sequential and combinational as a sketch. This slide here summarize what I said in the previous slide, because it says here a sequential circuit is specified by a time sequence of inputs, outputs, and internal states. It contains memory and just can remember the changes of input signals that occurred in the past. At the same time, inputs for the sequential circuit are functions of external inputs and the present state of the storage elements. Both external inputs and the present state determine the binary value of the output and the condition for changing the state of the storage state. So actually you can say output is a function of external inputs and present state, and next state is a function of external inputs and present state. This summarizes what we mentioned in the previous slide. In this slide, we are going back now to combinational circuit, where I'm going to give you another way to solve a combinational circuit. In the past, we gave you, in the other previous lectures, we gave you a function describing a function, and then you construct a truth table. From this truth table, you can get an equation. This equation you can use either K-map or identities in order to optimize your equation. But after that, you draw the hardware. Here I'm going backward. I'm going to give you the hardware and ask you to go back and give me the relationship between input and output. In order to do that, you have to follow certain steps like it's shown here in series, shown here in this slide, is the analysis procedures. The analysis procedure to obtain the output Boolean function from a logic diagram. First of all, you have the hardware, so you have to label all gate outputs that are a function of input variable with arbitrary symbol. Then from that you can determine the Boolean function for each gate. Number two, you have to label the gates that are functions of input variables and previous labeled gates with different arbitrary symbols. Then finds the Boolean function for these gates. The last one, repeat step 2 until the output of the circuit are obtained in terms of the input of the variable. So this means what? You have the hardware configuration. What you're going to do, you are going to label all the outputs for all gates inside this circuit diagram, and then you go forward from the input to the output. So you go level 1, level 2, level 3, and so on. For each level, you're going to find out a certain equation which is not the relation between out and input variable, and then until you reach the output. At the end, you can substitute and find out what is the relation between output A and the actual input values. This is going to show you in details in the next slide with an example. In this slide, we are going to apply what we mentioned in the previous slide about the analysis procedure. As you can see here, you have an input A, B, C, D, and you have two outputs F1, F2, and we need to find out the relationship between F1 and F2 as a function of A, B, C, D. First of all, as we mentioned in the first step, we have to label all outputs of the gates, which means here, as you can see in this figure, you have output of the first and T1, and then you have level 1, T1 and T2, and then you have for level 3, you have output of the OR gate T3, output of the XOR labeled T4, and output of the OR gate labeled F2 or T5. Actually, F2 equal T5, and then you have F1 output from the last level, which is the OR gate is F1. So now we have labels T1, T2, T3, T4, T5, and we have F1 and F2 as a function of the previous level and so on. So actually we are going to go forward. So going forward, which means we go from A, B, C, D for the level number 1 and level number 2, level number 3 and level number 4. Of course, level number 1, you can see two inverters, which means that you have B bar and C bar, and actually you can find out the output of the AND gate, the first AND gate, and as the upper one, T1 equal what? Equal B bar A, B bar C, and the output T2 equal what? Equal C bar A, C bar B. Sorry, equal A bar B. So now we know that exactly the T1 and T2 are functions of A, B, C, D. And then move to level 3, you'll find that T3 equal what? T3 equal T1 plus A, but actually T1 previously equal BC, B bar C. So actually you can say that T3 equal what? T3 equal A plus B bar C. As the same way, T4 equal what? T4 equal a bar B XOR with D. So actually T4 equal a T2 XOR D, which means equal a bar B XOR ma B, ma G. Okay, and then we have T5 equal T2 plus D, which means it's equal A bar B plus D. These equations we're gonna write it down in the next slide, but as you can see, I'm going from forward from in to out, and then you'll find that F1 equal T3 plus T4, which is equal to what? Equal equations which is defined by T3 and T4, and F2 equal T5. So actually you can find out the F1 at the end as a function of ABCD and F2 as a function of ABCD, and this will be shown in the next slide what I'm saying. So what we did at the beginning, we labeled all the outputs of the gates, and then T1, T2, T3, T4, T5, and we have F1, F2, and ABCD as inputs, and then after that we moved from in to out until we found out the relationship between F1 as a function of ABC and F2 as a function of ABC. So let us see in the next slide how this is done by equation. In this slide, we're going to apply what we mentioned in the previous slide regarding the analysis procedure. So as you can see here, we have T1 equal B bar C and T2 equal A bar B. Then you have T3 equal A plus T1. Substitute by the value of T1, it will be equal A plus B bar C. The same way, T4 equal T2 XOR D, which is equal to A bar B XOR with D, which will equal to A bar B D bar plus AD plus B D bar, B bar D. And then at the end you have T5 equal T2 plus D, which is equal to A bar B plus D, and then you can find F1 or F2 by substituting by the values of T1 or T2, T3, T4, T5. So actually you find out at the end F1 equal T3 plus T4, which is equal A plus B bar C plus A bar B D bar plus AD plus B bar D, and F2 equal T5, which is equal A bar B plus D. Actually, these equations can be simplified more by plugging it inside the K-map and then find out a way to find more optimized solution. So as when you did that, you find out that F1 equal A plus B bar C plus BD bar plus B bar D, which is actually at the last two terms as the XOR between B and D. So this means you can simplify the circuit diagram more and more by using the analysis, and then go from forward from in to out, find the equations from the function as a function of the input variables, and then you can use after that the K-map in order to reduce the circuit more and more as required. So this is actually another way of solving a digital system rather than giving you the idea and you go through it and find out the hardware. I'm here giving you the hardware and you are labeling all the gates output, and then you go forward from in to out to find the equation between F and input variables, and then you can use K-map in order to automate this. This is another way to solve a digital system as shown here. In this slide, we are going to give you another way to solve the same problem, the same example by using the truth table. In order to do that, I'm going to give you here the scenario or the steps to do that, and then we are going to apply it for the previously described example. First of all, you have to determine the number of input variables in the circuit for n inputs, and list the binary number from 0 up to power n minus 1. This is the actual way you are going to do the truth table. If you have n variable, you can have 2 power n combinations, and you start from 0 up to power n minus 1. Second step, you label all the outputs of the selected gates with arbitrary symbol, and this is symbols, and this is what you did in the previously in the last two 3 slides. And then you're going to obtain the truth table for the outputs of those gates that are functions of the input variables only, and after that you proceed to obtain the truth table for the outputs of those gates that are functions of the previously defined values until the columns for all outputs are determined. This is a scenario, or this is a steps in order to solve the truth table, but actually I'm going to apply it in the next slide for the example we mentioned before by using equation. Now we're going to use the truth table for it. So let me now apply what I mentioned in the previous slide for the example we mentioned before. Here I have ABCD. Actually, ABCD you have as long as we have 4 inputs, so you have 2 power 4, which means you have 16 combination from 0 up to 15. And then you start with T1. T1, as you can see here by tracing, you have to go through all the gates until you found T1 equal what, and then you found T2 equal, and then you found T3, and then you found T4, and then you found T5, and then F1, F2. As you can see, it's a headache, and there's a lot of errors you can do while doing that. So actually this procedure applies for some applications and does not apply for this example, because this the last example is much better to do by equation, and as long as you have the equation you can easily find out the K-map. And if you have the K-map, now you have the truth table, but it takes less time by doing it by equation rather than doing it this way by using the truth tables. I'm going to give you some examples after regarding solving the problem with a truth table, when it is applicable, when it's not applicable. But for this particular example, it's not applicable. As you can see, it's a headache and it has a lot of errors. Someone will by tracing will not get one input correct or one output correct, and so on. So it might give you a lot of problems, a lot of errors while doing that. So the best way to do it for this example is to use equation. Actually, in this slide, we are going to give you a brief about the design procedure, which is you're already doing it, but I'm going to give it to you here in wording. First of all, you have to form the specifications of the circuit, determine the required number of inputs and outputs, and assign a letter symbol for each. And then you need to derive the truth table that defines the required relationship between the inputs and outputs. And after that, you need to obtain the simplified, and take it from the word simplified, the simplified Boolean function for each output as a function of the input variables. And at last, you need to draw that logic diagram. These are the steps in order to design any circuit you're going to work with in the logic design, or any other circuit, by the way. It's not necessarily logic design, but still, but actually this is actually a generic and way to solve any problem, whether digital or analog or whatever. Now we need to say what we need to accomplish. Actually, when I'm going to evaluate your design, whether in the exams or quizzes or whatever, we need to accomplish minimum number of gates. We need to accomplish minimum number of inputs to a gate. We need to minimize the propagation delay of the signals through the gates, so propagation delay, which means the propagation from in to out. And we need to a minimum number of interconnections in order to avoid wiring and so on. This is actually the four important points which you need to accomplish when you design any digital circuit. Now let me go to example 2 and see what's going to happen in this example. In this example, I'm giving you a description of a certain function. Let us read it together. Design a combinational circuit with 3 inputs and 1 output. The output must equal 1 when the inputs are less than 3 and 0 otherwise. Use only NAND gates. Take care from these hints. Use only NAND gates. This means you have to design with only NAND gates. Anyway, let us first analyze this circuit. This is the description here. As long as you have 3 inputs, this means you have a 2 power 3, which means you have 8 combinations. So the first thing you do, you will have the truth table 0, 1, 0, 1, 0, 1, up to from 0 up to 7, and this is what's meant to be, and you have only 1 output. So you have to assign for all the inputs A, B, C, say, and you have the output A, F, whatever the function is. Now let me describe what's the condition inside this circuit. It says here the output will equal 1 when the inputs are less than 3. There are many solutions to solve these problems. The first one, you can say, is this 3 in decimal? So this means that the equivalent row, if it goes beyond 3, it will equal 3 and beyond it equals 0, and then 0, 1, 2 will equal 1. This means that if the number, the row number is less than 3, it will equal 1. Is greater than 3, it will equal 0. This is one issue. Another one will can say, okay, number of the inputs are less than 3, which means if you have less than 3 ones, it will give you 1, and if you have 3 ones, it will give you 0. Or someone will say if it has 3 zeros, it will give you 0, and then the rest will be basically 1. So actually, it is sort of a mini description for this function. You have 3 different ways. The first one, we are talking about the row number. So row number, which is a decimal. So actually, if the number less than 3, it will be 1, and if it is 3 and up, it will give you 0. Okay, and this is one description. The other one, we will look at 3 ones per row. If it is less than 3 ones per row, it will give you 1. Otherwise, this is 3 ones per row, it will give you 0. Another solution, if it is 3, if it is equal 3 zeros in a row, and then it's less than 3 zeros, it give you 1. So this actually is more than one way to analyze the circuit. If I don't say anything about what's meant by the inputs are less than 3, you have to solve the 3 different solutions. One for the row number, the second one for the number per ones per row, the third one the number per 0 per row. So this is actually, you have 3 solutions for that. Let me now consider to solve this problem with the decimal number. The row number is less than 3. So actually, if I do that, you find the truth table looks like that. You have x, y, z, the input 0, 1, 0, 1, 0, 1, 0, 1, up to 3 zeros, up to 3 ones. And you have the row number from 0 up to 7. So actually, as you can see, output F will be what? At 0 to 1, 2, it will equal 1, and when it is 3 and up, it will give you 0. So actually, this will be the actual truth table of such a circuit. But again, you have 2 different solutions, but here I'm considering only the one which is considering the number of the row number, which is decimal number, actually the equivalent decimal number. Okay, so this is actually what's in it. Now, if you solve this problem, you find that in this slide here, you can see This is the K-map for that truth table given in the previous slide. As you can see, the ones are there. The first group will give you X bar, Y bar. The second group, this group will give you X bar, Z. So actually the function if equal X bar, Y bar plus X bar, Z bar. You can draw it by and or, and then you can transfer, because as long as I mentioned him, you have to use only NAND gate. So what we did here, we have here a NAND gate by using bubbles. By using bubbles, you have to mix in simple notation for the NAND and invert all, and you find out the solution will be looks like that. So how many gates you have here? You have one 3x bar, which means that you have 3 NAND, and then you have another 3. Actually, here you have 6 NANDs. 6 NANDs. Why? Because X bar, Y bar, Z bar, they are inverted, but you have to transfer them again to the NAND gate. So you have 3 NAND gates, and then you have the two, the level 1, the 2 NAND gates, and then you have to invert all another NAND gate. So actually here you have 6 NAND gates, which means you need to have two NAND gates. This is a solution for that for this problem. As you can see here, you can draw it with and or, and then you can just use bubbles in order to transfer the and or to a NAND gate. I'm just going to give you here a small note that to put it in your mind. You must understand when a combination circuit has two or more outputs, each output must be expressed separately as a function of all input variables. Okay, because each one of output that has its own hardware. Yes, at the end they all combined in the same system, but actually when you describe it, you have to describe each one as a separate function. Thank you. Now in this example, I'm going to give you what's meant by code converter example. If I need to transfer, my input is BCD and my output will be XS3. This is actually not a converter. We can say this was an encoder, because we said when transferring a standard to non-standard is called encoder. So what we have here, we have ABCD as an input for BCD, and we have XS3 code, which is BCD plus 3. So actually you can see here, this is a description of the both codes in order to define the decimal number from 0 up to 9. Okay, so now we have 4 outputs, W, X, Y, Z, and you need to get each output as a function of A, B, C, D. Okay, so remember that you are here 4 inputs. 4 inputs, which means that you have 16 combinations. This means that we have 6 undefined states, 6 undefined states from 10 up to 15, and you have to use this as a don't care, as we mentioned in previous lectures. So now I need to build a circuit which is describing encoder transferring from BCD to XS3. So first of all, I need to search, is this something obvious here? We don't need for it K-map or not. As you can see here, Z is D bar. So actually what I have here, Z is D bar. So first of all, you don't need to do a K-map for Z, because Z actually, as you can see, obviously is D bar. Again, Y, as you can see here, if you go through it, we find that Y is the XNOR of C and D, because when it is even, you get 1. When it's an odd number of ones, you get 0. So actually, you can say here that Y is the XNOR of C and D, and this is obvious also. So we can there is no need to get the K-map for the Y. X and Z and W, I don't think there's any relationship that is obvious. So what we will do is X and Y, we're going to have a K-map for that. First of all, we need to find what's W equal to, and then you do the K-map for W, and then after that you do the K-map for X, and then you do a K-map for Y, and then K-map for Z. So actually you need to have 4 K-maps. So as I mentioned before, there is no need to do the K-map for Y and Z, because Y or Z are obvious, but I'm going to give you the K-map for it in one slide, but this doesn't mean that you have to do it. As long as it's obvious and clear, don't waste your time and waste your effort doing the K-map for something already obvious and clear to you. This slide here will give you the function W and X. As you can see here, this is a K-map for both W and X. And if you start with W, you find that you have one group is equal BC, second group is equal to BD, and the third group here is equal to A. So actually W equal A plus BC plus BD, which can be rewritten as A plus B multiplied by C plus D. As you can see here, I have used the don't care condition. The don't care condition for the BCD, you can find that you go from cell number 10 up to cell number 15, because the BCD is defined from 0 up to 9, and then from 10 up to 15 is undefined, which means you have a joker here from 10 to 15 in order to use. That's why I have reduced my hardware by using by taking advantage of the don't care, and I ended up with W equal A plus B multiplied by C plus D. Now let me go for the x. The x here, you have this group. This group will give you B bar C, and then we have the red group will give you B bar D, and then we have this group here of 2 will give you B C bar D bar. C D bar D bar. Actually, if you can see that x equals this equation, it can be reduced more by taking B bar as a common factor. So actually x will be equal to B bar multiplied by C plus D plus B C bar D bar. This is a x. For the other two, I said we don't need to do for the y and z, but I'm going to show it to you again. They are obvious, but I'm going to give you the KMAC for them as well. Actually, this slide here is redundant because, as I mentioned before, there's no need to draw the K-map for Y and Z because they are obvious from the truth table, but I'm going to do it here in order for you to prove that what I was saying before is exactly what is exists in the K-map. As you can see here for the Y, this group here will give you C bar D bar, and this group will give you CD. Actually, CD plus C bar D bar is equal to an x to null, which is C x to null D. And whenever you have even number of ones, you get 1. Whenever you have odd number of ones, you get 0. Okay, and this proves what I mentioned before in the obvious truth table. And now if you talk about Z, you find that this group of A, it will give you D bar, and actually this is also proves what we mentioned before about an obvious A solution. So this is actually, now we have 4 equations for the W, X, Y, Z. In the next slide, we are going to show you the equivalent hardware. This slide here gives you the logic diagram of BCD to XS3. It is not it's said code converter, but actually it is an encoder because we are transferring from standard to non-standard. So this is actually the hardware represented by the 4 equations we mentioned before in order to transfer or to convert or to encode BCD to its equivalent XS3 code. And this ends the lecture of April 13. And if you have any question, again, please communicate with us either through WhatsApp or through mail or whatever media is. We are available for you 24/7 if you have any question. In this slide, we're going to introduce to you a BCD to 7-segment decoder. BCD, as we learned from the previous lectures, BCD is binary coded decimal. Actually, what we do here, we have 4 digits or 4 bits where you can display from number 0 up to number 9. If you remember, 0 was 4 zeros and 1 0 0 0 0 1, and then the 9 is 1 0 0 1, which means that the BCD coded decimal is we have 4 inputs, and then the output will be 7-segment decoder of 7 leads. As you can see from the graph, the 7 leads are organized as shown. You have A small, B small, C, D, E, F, G. So if you have this type of layout, you will find out we can easily display on the screen numbers 0, 1, 2, 3, 4 up to 9. So what you can say here, the digital readout found in electronics calculator and digital watches use display devices such as light emitting diodes اللي هي بنسميها LED or liquid crystal display بنسميها LCD. Each digit of the display is formed from 7 segments. Each digit you have 7 segments, which means 7 LEDs. Each consists of one LED, okay, which is A, B, C. A is a LED, B is a LED, C is a LED, D is a LED, E is a LED, F is a LED, and G is a LED. All one crystal which can be illuminated by digital A signals. So we can control the layout, this layout, and lighting the variable you want, or the LED you want, in order to display the required number, as you can see in the next slide. In this slide, the truth table for the BCD to 7 segments is shown. As you can see here, we have 4 inputs, A, capital, B, and C, and D, and we have 7 outputs, A small, B small, C small, D small, E small, F small, and G small, which correspond to the LEDs used for the 7 segments. each one is an output. So actually what you have here, you have to have 7 maps and 7 equations in order to solve this problem. But here you should understand, as long as you have four bits, this means that you have 2 power 4, which means 16 combination. I'm using only 10 out of 16. So from 0 up to 9 is 10, and we have from 10 up to 15 is all outputs are undefined, are not used. Not used, it means that you have here don't care. If you remember from the past lectures, that don't care is a joker for us, so where you can use it either 1 or 0 based on the requirements, and which will give you the optimization for your hardware. But as long here I'm talking about a display, you cannot use the don't care but anymore. Don't care here should be 0, because if you don't want the screen to work, it's not valid. This means that the screen should be blank. Blank means it's 0, so here the don't care, you cannot use it as a joker. In this case, in this example, you have to have the display as 0. Because the 0 means that whenever the display is not working, it should be blank completely, nothing is working as a background. So here the don't care should be 0 for only this example, which we are talking about the display. We are not talking about anything else. So if the display is blank, it should be blank. As you can see, we have also seven equations. 7 equations will not be 100% optimized, because we are not going to use the don't care, because the don't care are zeros. So actually we are going to work with it as it is, and you can find in the next slide how by using the K-map what will be the 7 equations for the small a, b, c, d, e, f, g, and you will find how many gates you can have based on the outcome from the K-maps. This slide is actually give you the 7 equations for the A, B, C, D, E, F, G. Well, we got it from the previous slide from the twos table. As you can see, the twos table was constructed by having one under the value name of the LED that corresponds to the number you want to display. For example, if you have to display number 0, you have to have A, B, C, D, E, F. All of them are ones, except G in the middle should be 0 in order to display number 0, and so on for 1, 2, 3. So actually the twos table was constructed in that way. We cannot use the don't care here, because the don't care for the 6 binary combinations from 1, 0, 1, 0 to up to 1, 1, 1, 1. We cannot use 10 to 15, because these are not defined and actually will produce some meaningless or some arbitrary display arbitrary display of the unused combination, and we cannot do that, because we have to have a blank display if you are not getting the right number on the display. These equations, these are 7 equations. As you can see, it could include the 14 AND gate and 7 OR gates besides the 4 inverters. So as you can see, it is very complicated, and this is only for 1 digit. Assume just imagine if you need to have 2 digits, 3, 4, 5. For each digit you have to have this hardware in order to display number 0 up to number 9. The hardware will be given in the next slide. Looks like as a hardware. It's very complicated, as you can see, and this is only to display only 1 digit. Consider if we need to display more than 1 digit, how many the hardware would be much harder, and number of gates is huge, and so on. So this is to give you an example. If you need to display number 0 up to number 9 for the one display, this would be the hardware correspond to whatever the design is. This is actually an example for BCD to 7 segments, a 7 decoder. And as you can see, as long as you didn't use the don't care, the hardware is very complicated. In this slide, we are going to talk about arithmetic circuits. Remember when we talked before about you need to distinguish between logic operation and arithmetic operation. Logic operations, which means an OR gate, A plus B, which is an A or B. But if we talk about arithmetic operation, we're talking about 1 plus 1 equals 2, 2 plus 1 equals 3, and so on, but we need to do it in a binary A format. So actually, an arithmetic circuit is a combinational circuit that performs arithmetic operations such as addition, subtraction, multiplication, and division, which is either binary numbers or with decimal numbers in binary code. As you can see in this example here, we have 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, 1 plus 1 equals should be 2. 2 in binary is what? 2 is binary is 1, 0, because 0 under the column of 2.0 and 1 under the column of 2.1. So actually 1 plus 1 equals 2, you have 2 digits. This is the minimum possible hardware that you can have in order to add A plus B, but this is not complete set, so we call this one half adder. So combination set is that performs the addition of two bits is called a half adder, because as you remember in the previous lectures that we have to have a third input called previous input, because the carry that comes output from 1 plus 1 equal 1 0, you have 0 and carry 1. Carry 1 will go where? Carry 1 is added to the next higher order pair of significant bits. So this is actually in the second stage. You can have previous carry plus A plus B, which means that you have to have 3 inputs and 2 outputs in order to get what's called full adder, and we're going to discuss this all that in details in the next slides. As I mentioned in the previous slide, a combination set that performs the addition of 3 bits which means 2 significant bit and the previous carry is called a full adder. The half adder are employed to implement the full adder. The full adder circuit is a basic arithmetic component from which all other arithmetic circuits are constructed. This is actually a conclude what's mentioned in the previous slide, and we are going to implement that in hardware in the next slide. This slide here will give you an implementation for the half adder. Half adder, as I mentioned, we have 2 inputs and 2 outputs. So as you can see here in the twos table, we have x and y as an input and c and s as an output. S stands for the sum and c stands for the carry. So if we go on and do this by, you don't need actually here a K-map or anything else, because it's very clear that S is the XOR of x and y, and C is a x in AND gate between x and y. So there's no need to do any type of optimization or K-map or whatever. So this is what the half adder will looks like. As you can see here, it looks like S is x or y, which is x equal x bar y plus x y bar, and C equal x y, and this is the minimum hardware to build what's called the half adder. In this slide, we are going to build the full adder, the 3-bit full adder, because actually, as you know, a full adder is composed of 3 inputs, x, y, z, and 2 outputs, s and c. And actually, if you go to the twos table, as long as we have 3 inputs, this means that x, y, z will have 3 combinations, 2 to the power 3 combinations. So this means that you have 8 combinations, and by applying the rule of adding all them together, you will end up with S and C as shown in this twos table. You can use the K-map in order to find out what the equations are equal to, but as you can see here, C, the S column is actually the XOR of XYZ, because you know the property of the XOR. Whenever you have the row, number of ones per row equal to is even, you will get 0. Whenever the number of ones per row is odd, you will get 1. This is a property of XOR. So actually you can write S as X XOR Y XOR Z directly from the twos table, and you don't need to do the K-map. But if you do by the K-map, you will find out that X is the K-map looks like what you have in the slide, and S equal X bar Y bar Z plus X bar Y Z bar plus X Y bar Z bar plus X Y Z, which is actually at the end X XOR Y XOR Z, as I mentioned before. For the C, if you have the K-map for the C, you will find out that you have 3 groups here, which will end up C equal XY plus XZ plus YZ. These are the original equations where you can draw the hardware directly. But here I need to work as a small design. Small design means that you need to have a repeated or modular or a repeated hardware in order to get the best optimum design, as you can see in the next slide. So actually to do that, you have to unify the operator in your equation. As long as we have XOR with the S equation, you have to add XOR inside the C equation. The C equation here, you have XY plus XZ plus YZ. If you multiply YZ by X plus X bar, you did nothing, you didn't change the equation, because X plus X bar is 1, and anything multiplied by 1 is itself. But actually, I didn't do any changes to the equation. So at the end, C is equal XY plus XZ plus YZ multiplied by X plus a X bar. If you manipulate and you reorganize the equation, you will find out at the end C equal xy plus z multiplied by xy bar plus x by y, which is actually an XOR. So at the end you have the equation C equal xy plus z multiplied by x XOR y, and this is actually the two equations that governs the full adder. And you will find out that the hardware is given in the next slide, which will be very interesting when you see it in the next slide. In this slide here, you're going to see that this is the implementation of the two equations where after, of course, we did the smart design after adding the XOR in both equations, and you can see here it looks very familiar to you because this block here is a full half adder, and the other block here is another half adder. So actually you can say that the full adder is composed of two half adders together with an OR gate. So this is actually the implementation of a full adder hardware. The smart one, of course. This is a smart one composed of two half adders and an OR gate. Here we are going to add two numbers, a plus b, where a and b are 4-bit number. A 4-bit number, which means that a is from left 1011 and b from left 0011. So you have to align them in the columns in order to make sure that there is no empty space. Because if there is empty space, you have to add 0 at the leftmost or of the number. So here I have a plus b, so I have 1011 plus 0011. For the first column, you can use the half adder. There is no need to use the full adder, but in order to make it unified hardware, I'm going to use for all the full adder, because first column needed a full adder, the second one another one, the third one another one, and the third is the last one you need another one. This means that you need four full adders, because the one we described in the previous slides is only for 1 bit, or actually for one column. So a plus b. So actually what I'm going to do here, as long as for the full adder we have 3 inputs, the previous carry and a and b. For the first column I don't have the previous carry, so this means I'm going to put 0. So if you put 0, it will be 0 plus 1 plus 1 will give you what? Will give you 0, and you have the carry 1. What will happen here? A will go to the next column. If it goes to the next column, this means that we're going to add 1 plus 1 plus 1. 1 plus 1 is 0, I have carry 1, and then 0 plus 1 is 1, so actually the result 1, and A will have the carry 1. The carry 1 will go to the third full adder as the previous carry. So you have 1 plus 0 plus 0 will give you 1 and a carry 0. The carry 0 will go to the fourth full adder, and you have a 0 plus 1 plus 0 will give you 1 and you have carry 0. Okay, so now what happened here, if you go to hardware for this type of addition, you need 4 full adder in order to do this operation. For each column, you need 1 full adder. So after we have 4 full adder, and we're going to show you the hardware, what it looks like in the next slide. You can do it either in parallel addition, or you can do it as a serial addition, as we're going to mention and describe in the next slide. In this slide here, we are going to give you the hardware for the previous example, where we are going to add 2 numbers. As you can see here, I'm not using the numbers as binary, I'm using them as variables. You have A naught, A1, A2 is 3, and you have B naught and B1, B2, B3. So you need to add A naught plus B naught, and A1 plus B1, and A2 plus B2, and A3 plus B3. Each full adder, which is called here FA full adder, we have 4 full adders. One for the first column, the second column, the third column, and the fourth one. As you can see in the figure here, we are going to add them in parallel, so this is called parallel adder. Parallel adder, we have C naught. C naught should be 0 in order to, for the first column, as I mentioned, you can use a half adder, but instead of using half adder, we have used the full adder with an input A, C naught equal to 0. So C naught should equal 0, and A naught and A1, you will get a result as S naught, and the carry 1, C1 will go to the next A full adder, so you have C1 plus A1 plus B1, and the output will be S1, and the carry C2 will go to the third one, and so forth. So actually this is a 4-bit adder, and if you need to have 5, 6, 7, whatever, you have to add another a full adder, as you can see here. This is called a parallel addition because you have all of them are done at the same time. This is a very fast adder, but actually it's it needs a lot of hardware in order, because if you go from 4-bit to 5 to 6, 7, if you add only 1 bit, you have to have full adder. So can you imagine the size of the hardware you're going to use? So this actually is used only for small or medium calculators, okay, but actually if you need to use it for a larger number of bits, you can use what's called the serial addition. Serial addition means what? You have a full adder and a storage device, so you have to have a memory and only 1 full adder. It goes AI BI, CI, and then you get SI and ACI plus 1. So I goes from 0 and up, and actually this will be, you are using only smaller hardware. You have only one full adder, and you have a storage device in order to store the previous value and so on. But this is very expensive. Why? Because the storage device, the memory, is too expensive. So that's why the serial is a much higher in price than the parallel. The parallel, you need only a full adder, and you know the full adder is composed of two half adder and one OR gate. So this will be less expensive, but actually it needs a lot of a huge number of full adders in order to add extra bits. But for the serial one, you have only one full adder and a storage device. But the sum of the two n-bit binary numbers can be generated in serial or parallel fashion. The serial, I said, is more expensive. You have only one full adder with a memory, but as a parallel, as you can see from the graph here, you have four full adder, and if you need to extend, you can extend by using an extra full adder and so on. The parallel method use n full adders, and all bits are applied simultaneously to produce the sum. That's why it's faster than the other one. Again, if I need to do here, actually as you can see here, you can going now to play with this diagram now. This diagram, remember it and you memorize in your memory. You have four full adder devices, and you have A node, B node, A1, B1, A2, B2, A3, B3. So I'm going to play now with this device without doing any type of hardware or any type of KMap or stable or whatever. So let me now explore how I'm going to do in the next slide. In this slide, we are going to play now with the hardware we ended up with in the previous slide. Actually, we are going to exchange the full addition into full subtraction based on the complement of a number. Remember the complement of a number, we have two's complement and one's complement, and we use them in order to get rid of the negative sign. So the negative number here can be exchanged by taking the two's complement, one's complement, and then adding it to the positive number. We end up with a subtractor. So this is actually the way we're going to do here. If I'm doing that, the ones if you remember, you are just exchanging every 1 to 0 and 0 to 1, and this means that you're going to exchange all B's, the B node, B1, B2, B3, into B node bar, B1 bar, B2 bar, B3 bar. This is a negative number, the complement, the two ones complement of the negative number. And also, and we have to add the 1 to the least significant bit, which means I'm going to exchange C naught instead of initial value C naught equal to 0, C naught will equal to 1. So if I do that, you will end up by exchanging the whole operation from full addition into full subtraction. So actually, if I exchange C naught to 1 and I change every B to B bar, I end up by using the rule of the complement. The one's complement end up by subtraction instead of having addition. So we can say that the subtraction of a binary number can be done most conveniently by means of complements. The subtraction a minus b is done by taking the 2's complement of b and adding it to a. The 2's complement can be obtained by taking the 1's complement and adding 1 to the least significant bit, which is c naught. The 1's complement can be implemented easily with inverted circuit, and you can add 1 to the sum of by making the initial input carry of the parallel adder equal to c to 1, which is c naught. So actually, if we change c naught to 1 and exchange every b to b bar, we'll end up by full subtraction a. We did nothing with equation, we did nothing with too stable or anything else. We know the knowledge of the complement, and we know the hardware for the full adder, and we use this knowledge in order to switch the hardware instead of having full addition into having full subtractor, and this is a full 4-bit parallel subtractor. Now in this slide, if I need to combine both to make a choice, if I need to add, I'm going to add. If I need to subtract, I'm going to subtract. So I'm going to use the same hardware we mentioned in the previous slides, that's the 4-bit for adder. And what we did here, we make use of the property of the XOR. You know XOR property, if you have 1 with anything, it would be as a work as if you have an inverter, because 1 with A will give you a bar. And if you have 0 with A, will give you A, which means that XOR can work as a buffer or can work as an inverter. So if you do that and make use of the XOR, you find that we have added here the XOR for the hardware we mentioned before, and we have one input for the XOR is common, which is S selection line, and you have B node as your second input. So as you can B node are B1 and B2 obviously of course. So whenever S equal to 0, and S also is connected to C naught, to the initial value of the full adder. If S equal to 0, you find C naught equal to 0, and 0 with B naught will give you B naught, 0 with B1 will give you B1, 0 with B2 will give you B2, and 0 with B3 will give you B3. This means that you are going to do addition. If you need to do subtraction, you have S equal to 1, which means the initial value C naught will equal to 1, and 1 with B naught will give you B naught bar, 1 with B1 will give you B1 bar, 1 with B2 will give you B2 bar, and 1 with B3 will give you B3 bar, and this has happened to be the subtractor. So actually, if you need to subtract, you need to put S equal to 1. If you need to add, you need to put S equal to 0, and this is how we have built what is called the added subtractor circuit. And as you can see here, I did not use any truth table or any equations or K-maps or whatever. I just used my knowledge about the property of the XOR and the idea of having a subtractor and addition in the previous slides. I use this information in order to build my hardware, which is now an added subtractor circuit, which is very simple, and actually I did not make any effort for building that except for my knowledge building such a circuit. In this slide, we are going to use the knowledge which we have ended up in the previous slide, where we have a full addition and full subtraction based on the selection line S. When S equal to 0, you're going to add. When S equal to 1, you're going to subtract. Here I'm talking about BCD addition. If you remember the BCD addition when we mentioned it in the previous lectures, when adding two numbers in decimal coding, you have for each decimal number, you have 4-bit code. A 4-bit code, this is one column and column 2 and column 3 and so on. So I'm going to add, now I'm talking about only one column. One column means that you have to add a maximum of 9 plus 9, which is 1001 plus 1001 plus 1, which will be 19 at most. And now I need to add two numbers in decimal ABCD coding system. Coding system, which means that you have to have only from 0 up to 9. So actually the condition and the procedure and the scenario of adding in BCD addition, whenever the number is less than 9 or equal to 9, you add nothing to it, and when the number is greater than 9, less than 15, you add 6, and because you have 6 undefined states, you know exactly, as long as you have 4 bits here, you have 16 combination, and you are using only 10 out of 16, so the 0 up to 9 is your defined values, while from 10 up to 15 is undefined values. This means here that what you're gonna do is you have to have two full bit binary adder, one for collection and the other one for addition. The addition one, if you add the number again and the number is equal to the addition equal to 9 or less, you add 0, and if the number is greater than 9 and less than 15, you add 6, and if the number is greater than 16 than 15, you add 6 also. So actually you have to have the second full adder in order to make a collection, whether you add 0 or you add 6. So this is explained here by wording. An adder that perform arithmetic operation directly with decimal number system employ arithmetic circuit that accept the decimal numbers and present the results in the same code. It requires a minimum of 9 inputs and 5 outputs. 4 bits for the code in each decimal digit, and the circuit must have an input and output carry. When C equal to 0, nothing is added to the binary sum. When C equal to 1, binary 0, 1, 1, 0, which is 6, is added to the binary to correct the numbers, binary sum through the second 4-bit adder. Any output carry from the second binary adder can be neglected, and a decimal parallel adder that adds 2 in decimal digits need a BCD adder. The output carry from the BCD adder must be connected to the input carry of the adder in the next higher position. This means that what you're going to present in the next slide, you are going to present only how to add only one digit at a time. So we have to have A plus B, where A and B are decimal numbers encoding A decimal coding, which is A 4-bit plus 4-bit, and this is going to be explained in the next slide. In this slide, we are going to show you how to build a BCD adder. BCD addition, we have to understand the structure of the BCD first, and then you have to understand the scenario how to add two numbers in BCD coding system. The BCD coding system is composed of 4 bits, as you remember from the previous lectures, and you see from the table on the left hand side that you have 4 inputs A, B, C, D, and you have the weights 8, 4, 2, 1. The weights 8, 4, 2, 1 corresponds to power 0, to power 1, to power 2, to power 3, And you can see in black here numbers 0 up to 9 is a corresponding coding system shown in black. So 0 is for zeros and so on. So actually you can see here for a 0 up to 9 is defined, but as long as you have 4 inputs, you have 16 combination. But the 16 combination you are using only 10, which is 0 up to 9, but you are not using the 6A from 10 to 15 shown in red. So not used because you have a BCD code, and BCD is actually the natural number are from 0 up to 9. So actually number 10 is not there, number 12 is not there, because if you want to get 10 as a BCD coding, you have to have a code for 0 and code for 1, which means you have to have 8 bits. So this is actually unused or undefined states which you are not going to use in your hardware. You should skip that, and how to skip that? This is a from the scenario of adding two numbers. If you remember the scenario of adding two numbers in BCD coding system, you have a 4-bit binary adder because of the property of the BCD. You have 4 bits. So I'm talking about 4-bit binary adder. If you add these two, you get a result Z0, Z1, Z2, Z3, and the carry K. If you remember Z0 and Z1 and Z2, if the number here is less than or equal to 9, you have it as is. If the number is greater than 9 and less than 15, you have to add 6, which is an undefined state. So you have to add 6 in order to correct your answer. And if the number is greater than 15, which means the K equal to 1, this you have to add 6 also to to the results. So actually this is enforced us and let us at a you have to use another 4-bit addition. So for another 4-bit addition, the Z0 and Z1 and Z2 and Z3 are going to be the input for the second 4-bit binary adder, which is shown below here, and the second input will be fixed. It's either 0 or 6. So 0 whenever the number is equal to 9 or less, and 6 whenever the number is greater than 6 or than 9, sorry, or greater than 15. So you can see how to do that. As you can see here, the second input, we have two fixed lines with the first and the last one. The first and fourth one, you have 0 and 0, and you have the 2 in the middle connected to the output of an OR gate. The output C here, whenever C equal to 0, you get 4 zeros. Whenever C equal to 1, you get a number 6 with 0, 0, 1, 1, 0. So how we construct the hardware in between the two AND gate and the OR gate. Let me go back again to the table defining the BCD. The table defining the BCD, as you can see from 10 and for 10 and 11 in yellow, you have the second row, the second column, and the last one. They are always 1. So this means if you have an AND gate connected to the Z1 and Z3, which is the second and last one, this AND gate will be activated whenever you have numbers 10 or 11, and they give you 1. 1 will give you C equal to 1, and this will give you number 6. So this means that you're going to add 6 to the results. For the 12 up to 15, as you can see in green here, you have the last two columns equal to 1, which means here if you add AND gate between Z2 and Z3, this AND gate will be active whenever you have 12 up to 15, and this will activate the C to equal to 1, and C equal to 1 means that you're going to add 6 to the A results. The last one here, if the numbers is greater than 15, K will equal to 1. K is a carry from the upper 4-bit binary adder, and this K is equal to 1, which means it activates C again, and C will equal to 1. This will give you 6 again, and you can add 6 to the results. This is how we built the BCD addition, and as you can see, it came from your knowledge. You don't have to do any type of K-maps or equations or truth table or whatever. It actually came from your knowledge about how to build, how to add to BCD numbers, and what is the structure of the BCD coding system, and is the property of the and the property of the OR gate. Now we need to build what's called binary multipliers. The binary multiplier is very simple and very easy to handle, because as you can see in the structure, it goes without the scenario of multiplying two numbers to each other. The binary multiplier is the multiplier by each bit of the multiplier, starting from the least significant bit. Such multiplication forms is a partial product. Successive partial products are shifted one position to the left. The final product is obtained from the sum of the partial products. For J multiplied bits and K multiplied bits, we need a J multiplied by K AND gates, and J minus 1 multiplied by K bit adder to produce the product of J plus K bits. This is actually mentioned here in wording, but I'm going to show you in the next slide, which will be more understandable by graphs. In this slide, we're going to show you how to build a multiplier, binary multiplier. Actually, binary multiplier is very simple. We are going to follow the same rules for multiplying two numbers. If you have two numbers, a multiplied by b, where a and b are two-bit numbers, a naught and a naught a1, and b naught b1. And what you do in the scenario of multiplying, you get the least significant a naught and multiply a naught by b naught, and then a naught by b1. This is the first row, and then you have to shift to the left to 1 unit, and then multiply a1 by b naught, and then a1 by b1, and then you add the two rows together in order to get the results. The results actually will be 4 bits, because as long as you have 2 and 2, actually you have 2 plus 2 equal 4, which is the results will be always c0, c1, c2, c3, c3 for the carry at the end, because you are adding two numbers together. So this is actually how the structure of the multiplier looks like, and if you do it by hardware, you find out the need also. You need actually for the a naught b naught, you have an AND gate for a naught and b naught. The result will be always c naught, and then you need a naught b1 going into an AND gate, and you need a1 b naught going in another AND gate. These two, and the output of these two AND gates will go inside a half adder. The half adder will give you the result c1, and the carry from this half adder will go to the second half adder and will be added to what? Adding to 1 b1, and when it's added to b1 a1, it will give you c2, and the carry will be c3. This is the structure of the hardware. As you can see, it's very easy. There's nothing to do with equations. There's nothing to do with any type of truth table. But actually, what happened here, you got an answer by going through the scenario of multiplying two numbers and the knowledge of how to multiply two numbers. So we got the AND for AND gates. We have two half adder in order to build the hardware, and you can see here we built it in no time based on our knowledge of the A multiplication. In this slide, we are going to start with the decoder, but before I say anything about decoder, remember that when we talked about decimal coding system, we mentioned that for the decimal coding system, we have BCD, we have XS3, we have 2 4 to 1, we have 8 4 minus 2 minus 1, which means that some of them are standard and some of them are non-standard. The standard one is a BCD, of course, and the non-standard, the XS3, the 2 4 to 1, the 8 4 minus 2 minus 1. So actually, if we transfer from non-standard to standard, we call this one decoder. And if you remember, when we transfer from standard to non-standard, we call this one encoder. And we transfer from a non-standard, we call this as a converter. So let me now describe what's meant by decoder at large, because this will be a generic definition of the decoder. As you know, the discrete quantities of information, which is the actual information you have from your original information, the discrete quantities of information are represented in digital computer by binary code. So you have to transfer any information that comes from your mouse or from anywhere, you have to transfer it into a binary codes. So this is the first thing. The second thing, a binary code of n bits is capable of representing up to 2 power n distinct elements of coded information. This means that the truth table is a coding system, because the truth table, if you have 3 inputs, you can have up to 2 power 3, which is a number of combinations. So if you have any input for the truth table, you have 2 power n, and this is actually as if you have a decoder. So actually the truth table is a standard decoder, where you have, if you have 3, you will get you get 8 combinations. If you have 4, you get 16, and so on. So the truth table is considered as a decoder, as you're going to see next. A decoder is a combinational circuit that converts binary information from n coded inputs to the maximum of 2 power n unique outputs. So actually, this is actually, as I mentioned, if you have n coded system and if you have n inputs, you will get 2 power n unique outputs, and this is actually defined for the information. So as this is as we mentioned before, is a truth table configuration. A decoder has n inputs and m outputs, and is referred to as n by m decoder. Why we mentioned here n for m, and we didn't mention n and 2 power n, because sometimes we have a special case like what happened in the decimal coding system. In the decimal coding system, you remember, we have 4 inputs and 4 outputs. If you transfer XS3 to BCD, you have 4 in and 4 out. So actually, it doesn't mean if you're going to the standard decoder, you have to have 4 and 16, because 4n and 2 power n is 16. If you have 3, you have to have 8, and so on. So actually, this is a special case. So the decoder for the BCD, for the decimal decoding system, if transferred from XS3 or from 2 4 to 1 or from 8 4 minus 2 minus 1 to BCD, you have 4 in and 4 out. And as I mentioned, this is a special case of a decoder. and at the same time it will be special case of encoder and so on, because you have for in and for out always for the decimal coding system. But here for the general decoder you have to have n and 2 power n outputs. What we are going to describe in the next slide, actually we are going to describe the decoder with something called with enable input with NAND. Enable, which means that will give you the permission to have the output at a certain time, or does not give you permission. This is what meant by enable. But why using NAND? Because using NAND gate is here is very suitable, and actually sometimes the fabrication process and the use of NAND is a more appropriate than using AND and OR. And also it's more economical. So as you can see here, the enable input is using NAND. We have more economical to generate the decoder minimum terms with a sum product is there complemented from the using NAND. Support one or more enable input to control the circuit operation, which means it can disable when E equal to 1, no outputs, and E equal to 0 to works. So actually this is what we call a permission to do whatever you want to do. At the same time, it looks like a demultiplexer. We are going to give it to you in the next slides. So actually, demultiplexer is another the device that you're gonna use, and you're gonna illustrate what's meant by demultiplexer at the end of this slide. And also the meaning of demultiplexer is a circuit that receives information from a single line, and only one single line, and directs it to one of two and possible output lines. So this means that if you need to transfer the information from a single line, you can distribute this information up to 2n possible output lines, and this we're going to discuss it with you in the next slides. This slide here reflects what we mentioned in the previous slide. As you can see here, we have three inputs: E to enable, and we have A and B, and actually we have four outputs: D0, D1, D2, D3. Remember, at home we have something called receiver. Actually, the receiver is a decoder, because decoder means what? You have the provider are giving you free channels and are giving you subscribed channels. Free channels, which means anyone can watch. Subscribe, you have to have a password and you have to pay money for it in order to access the channels you want to look at a certain time. So here actually it's a customized decoder. It gives you this chance, I give you this idea. It's implemented by hardware. As you can see here, whenever E equal to 0 to 1, you don't care about A and B, which means A and B is your password. This means you don't need whenever you have A and B, X and X, this means there is no password to enter, and any channel can you can watch as long as E equal to 1. Whenever E equal to 1, this means that A has an open system, and the decoder is giving you the permission to see whatever comes on this receiver, except for the 4 channels in the home 0111. We have 4 ports here, 0111, and we have 1011, and we have 1101, and we have 1110, which is D0, D1, D2, D3. So D0, D1, D2, D3, actually, as long as you have 4 inputs, you have 16 combinations, but only 4 combinations are restricted, and the rest are open for you to see whatever. So that's what's happening here. Whenever E equal to 1, all the open combinations are free for you to watch the this channel. But whenever you have E equal to 0, you will find if you enter AB 00, which means the password for this type of this channel, you can watch the channel whose code is the code with the code of 0111. If you enter the AB, the password 01, you will get the A 1011. If you enter 10, you get 1101, and if you get 11, enter 11, you get 1110. So this is actually a way of the decoder in order to give you the restricted channels. You have to subscribe for it, and the open channel you can see free. This depends on the value of E. Whenever E is 1, so you have an open channels, you can see anytime. If the E equals 0, he's waiting for you to enter the right password in order to access the channel required at this moment. So this is the hardware here. As you can see, we have 4 LANs, and if you can see the E is going into inverter. This inverter is actually feeding all the LAN gates. So E exists in the all LAN gates. Whenever E equal to 0, you will find the inverter will convert it to 1. 1 over LAN will do nothing. So that's actually what the LAN gates are waiting for A and B to give them the permission. So when A, B, 0, 0 will give you channel 1, when A will be 0, 1 will give you channel 2, 1, 1, 0 will give you channel 3, and A 1, 1 will give you channel 4, and this is actually what's happening here. But whenever E equal to 1, you will find a converter with A, or the inverter will change it to 0, 0 over lamp will give you all the outputs ones as mentioned in the truth table. This is actually what we call a customized decoder in order to give you permission to see what you want to see based on the coding system, and this is what we call a password control system. As long as we mentioned that the decoder is actually truth stable, because the decoder you have n input and 2 power n of the output, the standard decoder is considered as if you have a truth table in your hand. So if you go to any hardware store and ask for a standard decoder, actually what he is giving you is giving you the truth table of your of the system. So now I'm going to use this decoder in order to build what's the full adder here. Remember that we did the full adder this before, and we mentioned it was different designs, and the full adder one optimized design was A2 half adders and OR gate, or you can use the original equation to build this function. But now I'm going to use the decoder in order to build a decoder and some OR gates in order to put the decoder use the decoder to build the full adder. So actually the decoder can be used to build any function. So this will be in the exams or quiz or whatever. I will ask you to do it on standard gates. I ask you to do it by NAND gates, by NOR gates, but whatever. But at the same time, I will ask you to build the system by using a standard decoder, and this is what I'm going to show you in the next slide. So remember this table here. You have X, Y, Z as an input. You have C, and S as an output, and we are going to use in the next slide a decoder to build the full adder with an OR gates. In this slide, as you can see, we are using 3 by 8 decoder, which is standard one, and we have the input X, Y, Z. Z is the least to power 0, and Y to power 1, and X is the most significant to power 2. And as you can see here, we have 8 outputs, which is from 0 up to 7. What happened here, I'm just choosing the positions where S equal to 1 or C equal to 1, and after that I'm using an OR gate. So it's very simple design, very easy design. What you are going to do is to buy a standard decoder and find out where is the position of the ones, and then there will be the input for the OR gate. The OR gate will give you the output, the required output you're looking for. So this is how we built the full adder by using a standard decoder with OR gates. As you can see here, it's very, very simple and very easy to use. Now, if you are talking about the encoder means you have a standard information and you need to transfer it to get a code for it, and non-standard. So actually, a decoder, you have 2 power n or less input, and you have n output lines. I'm talking about 2 power n or less. Why? Because if you remember the decimal coding system, we have 4 in and 4 out for the exchanging from BCD to XS3 or BCD to 241 or BCD to 841 That's why we said we don't need to use all the inputs. We need only for this special example. But here the encoder, the standard encoder is you have 2 power n or less input lines and you have n output lines. One of the famous encoder examples is the priority encoder. As you can see here, the priority encoder has its own function and its own description. I'm going to describe after giving you this example. If you go to the gas station, you can find that gas station is following what's called queuing system. Queuing system, first in, first served. But sometimes when there are ambulance or there are any police car, whatever, they have priority over everybody, so they can enter and cross the line and take their gas. This is what you call priority function. Each system, they have what's called queuing system or what's called a priority encoder. Here we are going to describe what's meant by priority encoder. Priority encoder is a combinational circuit that complements the priority function. The operation of priority encoder is such that if 2 or more inputs are equal to 1 at the same time, the input having the highest priority will take a precedence, and this will be done. It will be implemented first. And then, if you have for the next example or for the next slide, you have 4 inputs: D node, D1, D2, D3. So here I'm going to explain what's meant by the priority encoder by taking into example D3. The input D3 in the following truth table has the highest priority regardless of the value of the other inputs, which means If these three equal to 1, the output will indicate that the code A0 A1 equal 1 1, which means that A0 equal 1 1 means that any data appears in line 3 will have the priority, the highest priority, and will pass through the system irrespective of the other inputs. Now, if you're talking about D2, when D2 equal 1, D3 should equal 0 or must equal 0 in order to activate D2. When D2 equal 1, this means that the code A0 A1 equal 1 0, and this means that D2 has the highest priority in this case, and so on, and this we're going to explain in details in the next slide. Let me now start exploring to build the priority encoder by first of all drawing the truth table, and then from the truth table I'm going to get the equations. So let me first of all tell you how to build the truth table. The truth table is based on the definition of the priority encoder. It's not going through the standard way to build a truth table, because as long as you know the truth table, if you have D node, D1, D2, D3 as four inputs, you have to have 16 row based on 2 power 4. 2 power 4 equals 16. But here, and the first column should be 0, 1, 0, 1, 0, 1. The second column double 0, double 1s, and the third column would be 4 zeros, 4 1s, and then the last one would be 8 0, 8 1s. But actually, what's going to happen here, we are going to give you, based on the definition, we are going to build the truth table in different way. Of course, when the four zeros is exactly the same, but whenever you have D0 equal to 1, you should have D1, D2, D3 equal to 0, because D0 is the lowest priority. Again, and if we talk about D1 equal to 1, this means that D2 and D3 should be 0, and this D0, it doesn't matter if its value is, because you have to have here X. X means don't care, but don't care here, you have to consider both 0 and 1. So this means that you have here two rows, 0, 0, 1, 0 and 0, 0, 1, 1 exist in your table, because X here is not a joker. X is a joker only for the output, but inside the input, X is not a joker. You have to consider both values for X, which is 0 and 1. And now if we talk about D2, when D2 equal to 1, this means that D3 should be 0, and D0 and D1 are don't care. Don't care here means that as long as you have two X's, this means that you have four combinations. This means that you have here 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, and you have at the end of 0, 1, 1, 1. So this is actually, you have here four rows based on 0, 0, 0, 1, 1, 0, 1, 1. And then if you are talking about D3 here, when C3 equal 1, this means that D0 and D1 and D2 should all of them be exact, and this is what we have here, 3 X's. This means I have here 8 rows, which is starting from 0, 0, 0, ends to 1, 1, 1. If you count the number of rows, you find at the end you have 16 rows as expected. This is how to construct the truth table for the priority encoder. Regarding the output, as you can see here, we have A0 and A1 as a code, and we have another output called V. I will talk about V in a moment, but let me first explore what's A0 and A1 means. A0, A1, this is the coding system that is a password. Whenever A0, A1 equals 0, 0, this means I'm dealing with D0. When A0, A1 equal 1, 0, this means I'm dealing with D1. When A0, A1 equal 1, 0, this means I'm dealing with D2. When A0, A1 equal 1, 1, this means I'm dealing with D3. So this is how the code system is working. But actually here, as you can see in this table, we have a double 0, 0. Double 0, 0 means that you have a double coding system, and this is never happened. They cannot have a double coding system, so you have to differentiate between the 0, 0 by using the V output. The V output is actually V stands for valid or not. Validity, which means if V equal to 0, we don't care about A0 and A1 because all of them are equal to 0, and D0, D1, D2, D3 are all zeros. When V equal to 1, now we have to consider the value of A0 and A1. So when V equal to 1 and A0, A1 are 0, 0, we are dealing with D0. If V equal 1 and A0, A1 equal 1, 0, this means I'm dealing with D1. When V equals 0 and V equal 1 and A0, A1 equal 0, 1, this means I'm dealing with D2. When V equal 1 and A0, A1 equal 1, 1, this means I'm dealing with D3. This is how we construct the table, and now it's time to build the hardware. In order to build the hardware, we need three equations, a V for V, A0 to A1. For all of them are function of D0, D1, D2, D3. So what I'm going to do, I can see that V is actually obvious. It's an OR gate. So V equal D0 plus D1 plus D2 plus D3, and it's very obvious. and so this is an OR gate. And then if talking about A0 and A1, you can find the K-map is shown below. If I'm talking about A1, A1 has 2 ones in the column, but actually these are not 2 ones, they are 12 ones. 12 ones, why? Because the first one is corresponds to the line 01XX. 01XX means I have 4 cells here, which means that this one is located in cell number 4 up to cell number 7. And for the last one, it corresponds to the row 1XXXX. This means that it exists in 8 cells, and it starts from cell number 8 up to cell number 15. So these 2 ones actually exist from cell number 4 up to cell number 15 as shown in the K-map. If I'm talking about a node, you will find that the first one also is located at corresponds to the row 001X, which means you have 2 cells here. So one is located in cell 2 and cell 3, and the last one located in the 8 cells from cell number 8 up to cell number 15 as shown in the K-map below. And now I'm going to build the equations. Since the P equal D0 plus D1 plus D2 plus D3, and A1 you can find here is this is D3, and this group corresponds to D2. So actually A1 equal D2 plus D3. And for A0 you find that this is D3, and this group here will give you D2 bar. So A0 equal D2 bar plus D3, and these are the equations governing the priority encoder. And the next slide, I'm going to give you the equation. As I mentioned in the previous slide, as you can see, A0 equal D3 plus D1 D2 bar, and A1 equal D2 plus D3, and B equal D0 plus D1 plus D2 plus C. So in order to build this function, we find that this is the hardware that reflects the priority encoder, and doing it with or and or not. Actually, you can do the same thing for this one by using decoder, but using any type of hardware. But this is actually the 4-bit priority encoder I mentioned in the previous. In this slide, we are going to introduce a multiplexer. It is a special type of decoder. As you can see here in the figure, that you have 2 power n inputs and you have only 1 output, and you have n selection lines. What does it mean? As you can see from the description here, the multiplexer is a combinational circuit that selects binary information from one of many lines and directs it to a single output line. So you have only one active line at a time. So you can how to select that. The selection of a particular input line is controlled by a set of selection variables, which is the n input selection line. So the n input selection line will give you a code. This code will activate one of the ports, which is one of the 2 power n, to be directed to the output the single output, as you see from the figure. Normally there are 2 power n input lines and n selection variables whose bit combination determine which input is selected. Also, as in decoder, multiplexer may have an enabled input to control the operation of the unit, and when the enabled input is in active state, the output are disabled, and the enabled input is useful for expanding 2 or more multiplexers into a multiplexer signal, a multiplexer with a larger number of inputs. This is the brief description about the multiplexer, but in the next slide, we are going to give an example to understand clearly what's meant by multiplexer. As I mentioned, the multiplexer, you have 2 power n input, you have only 1 output, and you have n selection lines where you activate only one of the 2 power n inputs to be active and go to the output port. In this slide, I'm going to give you example. It's a very simple one. We have 4 inputs, which means that we have 2 power n equal 4. So this means I have to have 2 selection lines, and I have 1 output 1. As you can see here, we have D0, D1, D2, D3 as an input, and we have S0 as S1 as the selection lines, and we have a Y, and Y as an output here. Assume that S0, S1, this is the selection line, this is what AFS. If you have S0, S0, S1 equal 0, 0, this means that only one of these 4 ANDs will be active at a time, because S0 and S1 are connected to all AND gates. So you have the 2 inputs for the selection line, and you have only 1 input with D0 going to the upper AND, D1 to the second one, D2 to the third one, and D3 to the fourth one. So actually, if you can see that, you can see that S0, S1 is either 0, 0, 0 1 1 0 1 1. So if you have S0 S1 0 0, this means that the upper end will be active and all other ends are disabled, which means that only D note will go through and go to 1. If S0 S1 equals 0 1, this means that the second end from the other from up yani from the top, the second end it will give you is reactive and all the other three ends are disabled, which means D1 will go to Y. And if you have S0 S1 1 0, this means the third end from top will be active and the other three ends are disabled, which means are equal to 0. This means that D2 will go through and go to the output. And if we have S0 S1 1 1, we will find out that D3 is active, which means that the last end is the lower end is active and all three ends are disabled. This means this 3 will go through and go to 1. This is what's meant by a multiplexer. As you can see, we have 4 by 1, which means that we have 4 inputs, but only one is active at a time, and this is the purpose of having a multiplexer as a function. As long as we have used a decoder as a device that you can build any function with, because the decoder is actually truth table, here I'm going to give you a way to use the multiplexer to build any function by using any type of a multiplexer. Implementing a Boolean function of n variables, we have n minus 1 selection lines. What it does is the first n minus 1 variables of the function are connected to the selection line, selection input of the multiplexer. The remaining single variable of the function is used for the data inputs. This we're going to explain in the next slide with an example. If the single variable z is z, the data output of the multiplexer will be either z bar 1 or 0. This is going to be clarified and shown in the next example to understand what is written here in this slide. As an example here, we have a function f and we have inputs x, y, z. So actually I'm going to use 4 by 1 multiplexer in order to build this function. We can use 8 by 1 multiplexer, we can use 2 by 1 multiplexer, but this one I'm going to use 4 by 1 multiplexer. If you want to use 8 by 1, all you need to do, you have x, y, z selection lines, and you have the output f as it is, 0, 1, 1, 0, 0, 0, 1, 1, and this will be your input for the multiplexer, and the output f will be as expected, because if you have x, y, z equals 0, 0, 0, you will get 0. If you have x and y and z equals 0, 0, 1, you will get 1, and so on. So actually this is called 8 by 1 multiplexer, but here I'm going to use 4 by 1 multiplexer. Using 4 by 1 multiplexer, this means I'm going to have the most significant variables x and y as a selection lines. So we have S0 and S1 is y and a, y and x, and we find what's the relationship between z and f. So we have here 4 blocks. Instead of having 8 lines, we have here 4 blocks. One block is x and y equals 0, 0, and the second block x and y equals 0, 1, and the third block x and y equal 1, 0, and the fourth block x and y equal 1, 1. So whenever x and y equals 0, 0, this is a relationship between f and z. You find that f equals z. And for the block x, y equal 0, 1, you find that f equals z bar. And for the block x, y equal 1, 0, we find that f equals 0. And for the block x, y equal 1, 1, we find that block equal f equal 1. So actually, if you have the multiplexer as a block diagram here, you find that we have x and y as a selection line, and we have in port 0 z, in port 1 z bar, in port 2 0, and port 3 you have 1. So whenever the value of x and y is, you can get a port 0 or port 1 or port 2. So make sure of the orientation. They should go exactly like the one you have in the truth table, in order to make sure that whenever 0, 0 is there, you find that f exactly equals z, and whenever xy equal 1, 0, you can find that the f equals z bar, and so on. This example will explain to you what's meant by a multiplexer. Just the general steps for doing that, you have to go through the steps which is written here in this slide. First, the Boolean function is first listed in the truth table. The first n minus 1 variables listed in the table are applied to the selection input of the multiplexer. For each combination of the selection variables, we evaluate the output as a function of the last variable. This can be 0 or 1, the variable, or the complement of the variables. This is actually the steps describing what we did in the previous slide, and as you see, we sometimes call the multiplexer MUX. MUX stands for multiplexer. The opposite functionality of the multiplexer is called demultiplexer. Demultiplexer, it is a digital function that performs the inverse operation of the multiplexer. It receives information from single line and transmits it to one of the two power n possible output lines. And this is done by the selection of a specific output is controlled by the bit combination of n selection lines. This means that I have only one input and n selection lines, and I have multiple output, and this output I will direct the input to one of them based on the n selection lines, as you're going to see in the next slide for description. In this slide here, it shows you the demultiplexer, 1 to 4 demultiplexer. As you can see, you have E as an input, goes to the all AND gates, and you have the S0 and S1 as usual selection lines going into all the AND gates as first S0 bar S1 1 bar 0 0 0 1 1 0 1 1. So whenever the value of and we have a full output seal, D0, D1, D2, D3. So based on the value of S0 and S1, E will be directed to one of these output based on your selection. So if you have 0 0, this means E will go to D0. If you have 0 1, E will go to D1. If you have 1 0, E will go to D2. And if you have 1 1, E will go to DC. This is what is called the demultiplexer, and it is the opposite functionality of that multiplexer.